Welcome, curious minds and sleepy thinkers. You've found a soft place to land where the questions are big and the pace is slow enough not to jolt you out of your pillow cocoon. Tonight, we're going to tiptoe into one of the most mysterious questions ever asked by those who gaze upon the distant lights of the cosmos. We'll drift through the strange fleeting flashes that appear blaze with an impossible brilliance and then vanish as quickly as a dream upon waking. But don't worry, we'll take it slow. This isn't a race through equations. It's more like floating through a galaxy of ideas with a cup of chamomile tea. We'll simply let our minds wander through the vast, dark ocean of space, listening for the faintest whispers from phenomena so grand they challenge our very understanding of what's possible. Imagine, if you will, the deepest night. Not the kind of night under city lights, but a true pristine darkness far from any earthly glow. Above you, the Milky Way stretches like a milky river studded with countless diamonds. Now, within that profound stillness picture, an unexpected blinding pulse of azure light. It appears without warning, a brilliant cerulean blossom unfolding in the cosmic garden, momentarily outshining everything around it. This isn't a star nor a familiar explosion. It's something else. Something so vivid, so startling, that it makes even the grand spectacle of a supernova seem like a distant, faintly lit candle flickering in the immense, silent expanse. This is the luminous fast blue optical transient, or LF-BOT, a name that in its very syllables hints at its fleeting, vibrant, and utterly baffling nature. For years since the calm year of 2018, these celestial whispers, these sudden shocking flashes of blue, have been caught by our watchful eyes here on Earth. Some have been incredibly close, astronomically speaking, a mere breath away in the cosmic sense. Others have appeared from distances so vast, so mind-bendingly far that their light began its journey billions of years ago, long before our sun even existed, traveling across an expanding universe to finally kiss the sensors of our most sensitive telescopes. Yet, despite these incredible distances and the immense stretches of time, they all bear a striking resemblance. They are kin somehow, these vibrant bursts, sharing a common bewildering signature. But the deeper mystery, the one that truly sets the mind adrift, is this: no one truly knows what they are. We do not fully grasp their origin, nor the cataclysmic events that summon them into being. The data so far has been a thin, delicate thread. Being such a fresh entry into the cosmic lexicon, LFOBOTs are still largely unmapped territories in the grand atlas of astrophysics. It was only 6 short years ago, in 2018, that the very first of these elusive flashes was firmly identified. Since then, we've only managed to glimpse a handful more. This scarcity of observations, this mere handful of shimmering moments, casts a long, thoughtful shadow over our efforts to truly define them. How does one categorize something so rare, so fleeting, so utterly unique? For now, the scientific community, in its collective wisdom, has settled on a few shared characteristics, common threads that weave through the fabric of each observed LF-BOT. They all paint the sky with a predominantly blue hue, a deep striking sapphire. Their optical luminosity is extraordinarily high, a beacon that outshines nearly anything else in the universe, and their brilliance isn't confined to the visible spectrum. They blaze brightly in X-rays, in ultraviolet light, and even send out powerful whispers in radio waves echoing across the void. But the most defining trait, the one that gave them their very name, is their breathtaking speed. These LFOBOTs are like a cosmic camera flash, reaching their blinding peak brightness in an instant, and then just as swiftly, they begin to dim. This fading happens with astonishing rapidity, often within the span of mere hours, or perhaps a few short days. It's a stark contrast to the familiar death throes of a supernova, which, while also brightening and then dimming, does so over a leisurely period of weeks, or even months. Imagine a grand celestial firework that explodes and then vanishes before you can truly grasp its form. This brief, ephemeral nature, this blink and you'll miss it quality, is what makes LFOBOTs so incredibly difficult to spot, and consequently, so challenging to study. They are the shyest, most fleeting dancers in the cosmic ballet. So how, you might gently wonder, did we manage to capture such an elusive event? How did we, with our earthbound instruments, manage to pinpoint such a rapid distant flash? The answer lies partly in a network of watchful eyes instruments designed for other purposes, but constantly scanning the heavens. One such sentinel is NASA's Atlas HKO telescope, nestled on the quiet slopes of Hawaii. Its primary mission, its silent vigil, is to serve as an early warning system for asteroid impacts. Night after night, it methodically sweeps the entire sky, sometimes several times over, searching for any moving objects that might pose a threat to our home world. It's a relentless, unwavering gaze, a quiet guardian. And it was during one of these routine methodical scans on a quiet day, June 16, 2018, that Atlas HKO captured something truly extraordinary, something that defied its usual expectations. A flash, a sudden burst of light that blazed an astonishing 100 times brighter than a regular supernova. And then, just as remarkably, it was gone within days. The news rippled through the scientific community, not with a clamor, but with a quiet, intense urgency. The scramble was on. Scientists, their minds alight with curiosity, immediately began to pore over the data, sifting through the luminous echoes to understand what grand, unprecedented event they had witnessed. They meticulously traced the explosion's origin, pinpointing it as coming from the ancient familiar constellation of Hercules, a staggering 180 million light-years away. This event was officially designated AT-2118 Cow, and with a touch of cosmic whimsy, it was affectionately nicknamed the Cow, a nod to the last 3 letters in its formal designation. Once its location was settled, it was quickly and perhaps a little too readily classified as a Type 1b supernova. This particular kind of supernova, often referred to as a core collapse explosion, is born from the dramatic demise of massive stars, those colossal celestial giants that at the end of their lives succumb to the immense crushing force of their own gravity. But as with all great mysteries, the initial classification, the neatly labeled box, soon began to feel uncomfortable. Something about this particular explosion, the Cow, didn't quite fit the established narrative. When the scientists took a closer, more discerning look at the Cow's emission spectrum, the unique fingerprint of its light, it simply did not conform to the typical characteristics of a Type 1b supernova. It presented unusually broad emission lines, like the blurred brushstrokes of a cosmic artist, and surprisingly, very weak helium lines, almost as if a crucial ingredient were missing from its stellar recipe. This unusual signature stirred a memory, a faint echo of another rarer kind of supernova, a Type 1cBl. So, with a thoughtful reevaluation, the Cow was reclassified, once more placed into a slightly different, though still familiar category. Yet the more these dedicated astronomers delved into the vast ocean of data, the more surprised and perhaps a little bewildered they became. Whatever this explosion truly was, it began to look less and less like any supernova they had ever encountered. At least not the kind of supernova they had come to expect, the kind that fit neatly into their well-established models. For starters, it appeared out of nowhere, a true cosmic ghost. This blast went from being utterly inactive, a silent void, to reaching its peak luminosity in just a few short days. Remember, the grand familiar supernovae usually take a much more gradual path, unfolding over a few months to reach their brightest point and then dimming at a similarly measured pace. The Cow was a bolt from the blue, a sudden shocking crescendo, and it wasn't just its speed that was perplexing. The sheer overwhelming brightness of the Cow was also a profound anomaly. It registered as 10 to 100 times brighter than an ordinary supernova, a blazing beacon that seemed to defy the known limits of stellar explosions. It was as if a familiar melody had suddenly erupted into an impossibly loud, vibrant symphony. But beyond the astonishing speed and the blinding luminosity, there was another, even stranger piece of the puzzle. Everything about the way it exploded seemed wrong. When supernovae traditionally unleash their energy, they tend to do so in a beautifully symmetrical spherical shape, like an expanding bubble of light and force. We have since learned, of course, that the shockwaves sent out after a supernova can sometimes be aspherical, a little distorted, often due to the powerful presence of strong magnetic fields within the dying star, which can subtly warp the initial blast. However, upon even closer, more meticulous inspection, this particular mystery explosion, the cow did not even explode with this expected, though occasionally distorted symmetry. The very researchers who studied it with a note of awe in their reports described it as the most aspherical explosion ever seen. Imagine a cosmic balloon inflating, but instead of a smooth sphere, it pushes out in jagged, uneven bursts, defying all expectations. Such profound defiance of known physics naturally leads to fertile ground for new ideas, new ways of seeing the universe. Soon enough, other theories began to gently surface whispered possibilities in the quiet halls of astronomical debate. Some brilliant minds suggested that the cow might be the result of a monstrous black hole, a truly colossal cosmic vacuum cleaner aggressively shredding a passing star. Imagine a star innocently drifting by, suddenly caught in the irresistible gravitational embrace of a supermassive black hole, its very fabric being torn asunder in a spectacular final gasp of light. Others proposed a different, equally dramatic scenario. Perhaps it was a supernova, but one that gave birth to something new and incredibly dense. A black hole or a neutron star leaving behind this bafflingly bright, fleeting signature. But let's step back for a moment and allow ourselves a pause for contemplation. It's incredibly challenging, isn't it, to draw any firm, sweeping conclusions when you only have one of something. It's like trying to understand the entirety of an ocean from a single drop of water. As the timeless saying goes, once is an anomaly, twice is a coincidence, and 3 times is a pattern. What these dedicated researchers truly needed, what their minds yearned for, was a larger sample size, more instances of this mysterious bright blue explosion. They needed more data points, more whispers from the cosmos, so they could compare observations, look for subtle similarities, and perhaps, just perhaps, deduce any hidden patterns that might arise from the depths of the unknown. The universe, in its own mysterious way, often reveals its secrets slowly, one glimmer at a time, allowing us to piece together its grand, intricate tapestry. And so, the waiting began, a hopeful vigil for another fleeting flash of blue. This initial encounter with the cow, this first LF-bot, was more than just an observation. It was an awakening. It gently pushed the boundaries of what astronomers thought they knew about stellar death and explosive phenomena. It highlighted the sheer unfathomable complexity of the cosmos, reminding us that even in the most well-studied corners, there are still vast uncharted territories of understanding. The cow, with its perplexing speed, its defiant luminosity, and its shockingly asymmetrical explosion, was a cosmic enigma that refused to fit neatly into any pre-existing category. It was a beautiful, terrifying reminder of the vast ocean of unknown physics that still surrounds us, a quiet invitation to humble ourselves before the grandeur of the universe and to embrace the thrilling discomfort of not knowing. The questions lingered like distant starlight. What force could possibly generate such a blast so quickly, so brightly, and then extinguish it with such haste? Was it a new kind of star dying in a way we had never conceived? Or was it something far more exotic, a dance between celestial giants that produced a fleeting, blinding spotlight? The theories were mere conjectures, threads cast into the cosmic wind, hoping to catch on to some hidden truth. Each new observation, each subtle detail gleaned from the faint, lingering echoes of the cow's light, only deepened the mystery, peeling back layers to reveal even more profound questions beneath. The scientific journey, after all, is not just about finding answers, but about discovering ever more profound and beautiful questions to ponder. And the cow, in its brief, brilliant life, had offered a treasure trove of them, inviting astronomers on a thrilling new quest into the heart of the universe's most luminous secrets. It was a testament to the fact that even when we think we have mapped the known, the universe always has another surprise, waiting, another stunning revelation, poised to shatter our preconceived notions and expand the horizons of our wonder. And so the quiet anticipation continued, a collective breath held, waiting for the next blue whisper from the depths. Luckily, it didn't take long for scientists to get their eyes on a second similar explosion. The universe, it seems, has its own rhythm of unveiling secrets, often at just the right moment. A mere few months later, in September 2018, the cosmic camera flashed again. Another brilliant fleeting bloom of blue light erupted in the vast, silent canvas of space. This second event, much like the first, captivated the minds that observed it, stirring both recognition and a renewed sense of wonder. It was confirmation, a gentle nod from the cosmos, that the cow was not an isolated anomaly, a singular cosmic quirk, but perhaps the first in a family of entirely new phenomena. And then, for a third time in the quiet year of 2020, the universe delivered another such whisper. This time, the flash was equally vivid, equally ephemeral, completing a trio of bewildering events. Keeping in the charming tradition of pulling animal nicknames from the last three letters of their official designations, a delightful, almost whimsical LF bot zodiac began to take shape in the minds of the astronomers. The pioneering cow was now joined by the enigmatic koala, its light echoing across unimaginable distances, and the steadfast camel completing the initial set of these peculiar cosmic transients. And just like that, what was once a solitary, inexplicable event had now blossomed into a modest, yet invaluable collection of data points, 3 separate LF-bot events. This small, precious sample size was exactly what the researchers had yearned for, exactly what they needed. With 3 distinct occurrences, they could finally begin the crucial hunt for patterns, those subtle, recurring threads that weave through the fabric of cosmic events and hint at underlying universal laws. It was a moment of quiet triumph, a collective sigh of anticipation as the journey from anomaly to potential understanding truly began. When the dedicated teams of astronomers began the meticulous process of analyzing the cow, the koala, and the camel, sifting through the luminous data with patient, discerning eyes, one of the very first things that gently rose to the surface, one of the most striking commonalities, was the location of these mysterious events. Even though each of these brilliant flashes had erupted in vastly different corners of the universe, separated by billions of light years and immense stretches of cosmic time, every single blast was consistently registered as originating from within the spiral arm of a galaxy. Imagine, if you will, the grand swirling arms of a colossal pinwheel, painted with stars and dust. It was always within these luminous active ribbons of cosmic material that these LF-bots made their fleeting appearance. At first glance, this intriguing piece of information, this subtle celestial clue, seemed to breathe new life into the initial theory, the one that suggested LF-bots were merely a particularly energetic or unusual type of core collapse supernova. Let me explain why this seemingly simple fact, this consistent location, felt like a comforting validation to the astronomers. You see, the kind of star that undergoes a core collapse supernova is a truly massive gargantuan star. We're talking about the titans of the cosmos, stars that dwarf our own sun by many, many times over. And as you might intuitively grasp, the bigger the star, the more furiously it burns, consuming its nuclear fuel at an incredibly rapid rate. This intense fiery existence means that these colossal stars have a tragically short lifespan, a mere cosmic blink compared to the billions of years our sun will patiently endure. They simply don't get the chance to travel very far from their birthplace before their fuel runs out and their majestic lives come to a cataclysmic end. It would then make perfect sense, a logical conclusion in the grand cosmic narrative, that their supernovae would occur very close to the dense star clusters where they were born, where they first ignited their brilliant fires. And what part of a galaxy, dear listener, is famously known for harboring such vibrant, active star-forming regions. These bustling nurseries of colossal short-lived stars. Yes, you've guessed it. It's precisely the spiral arms, those luminous active regions brimming with gas dust and the raw ingredients for new stellar generations. These are the very cosmic neighborhoods where young massive stars are plentiful, where they live their brief glorious lives, and where they ultimately meet their dramatic explosive fates. The exact place, mind you, where all three of our mysterious LF bots, the cow, the koala, and the camel, had been observed to burst into fleeting brilliance. For a moment, there was a quiet collective sigh of relief in the scientific community. The pieces seemed to be falling into place, fitting snugly into a familiar puzzle. The LF bots, despite their bewildering brightness and lightning-fast fades, could still be accommodated within the existing framework of stellar evolution and death. It was a comforting thought, a gentle reassurance that the universe, even in its most spectacular displays, still adhered to the grand, elegant rules they had diligently worked to uncover. This correlation with spiral arms, this seemingly simple pattern, felt like a steady hand, guiding them through the initial fog of uncertainty. The discovery of this common location provided a much-needed anchor in the churning seas of astronomical anomaly. Before this, the LF bots were like rogue waves appearing from nowhere, defying expectations. Now, with the spiral arm connection, they seemed to be part of a larger, more comprehensible current. It allowed the scientists to feel a fleeting sense of mastery over the unknown, a satisfying click in the mental machinery of understanding. This pattern allowed them to begin building a tentative but plausible theoretical framework, a conceptual scaffold upon which future observations could be hung. It was not a definitive answer, no, but it was a promising direction, a pathway illuminated by the repeated whispers from distant galaxies. The initial bewilderment began to recede, replaced by the calm, focused pursuit of deeper insight. The very idea that these immensely powerful, yet incredibly fast explosions could be linked to the birthplaces of the most massive stars offered a comforting elegance. It meant that despite their outlandish characteristics, LF bots weren't entirely alien phenomena. They were perhaps just an extreme manifestation of something already understood, the violent, beautiful end of a cosmic giant. This hypothesis, rooted in the familiar stellar life cycle, felt like coming home after a long journey into the bewildering unknown. It provided a sense of order to what initially seemed like pure chaos. The universe, in its intricate dance, often reuses its fundamental elements, just in different, sometimes more dramatic configurations. And here, in the spiral arms, it seemed to be playing out a familiar, albeit amplified crescendo. The scientists, in their quiet observations, felt a surge of renewed optimism. The initial classification and reclassification of the cow had been a frustrating dance with ambiguity. But now, with the koala and the camel joining the fray and all three pointing to the same galactic addresses, the prospect of a unified theory, a single explanation that could encompass all these dazzling events, seemed within reach. The grand tapestry of the cosmos, which had felt so frayed and torn by these enigmatic flashes, began to reweave itself into a more coherent and beautiful whole. The spiral arms, those nurseries of massive stars, were now being viewed not just as sites of birth, but also as potential epicenters of these blinding, enigmatic deaths. It was a compelling narrative, a story that felt right-fitting seamlessly into the established lore of the universe. This period was one of quiet breakthroughs, where the incremental accumulation of data began to yield conceptual leaps. The confirmation of a pattern, however subtle, provides the crucial momentum for scientific inquiry. It transforms a scattered collection of anomalies into a focused quest for a deeper, more profound truth. The astronomers armed with this nascent pattern felt a renewed sense of purpose, their patient vigil rewarded with a tantalizing glimpse into the mechanics of these cosmic marvels. They could now refine their models, ask more targeted questions, and most importantly, know where to look next for more of these elusive blue flashes. The universe, it seemed, was slowly beginning to reveal its secrets, one spiral arm at a time. Imagine for a moment the meticulous work involved in piecing together such a cosmic puzzle. Each photon captured each spectral line, analyzed each tiny flicker of light, becomes a crucial piece of evidence. The scientists working with data from telescopes like Atlas HKO are like detectives gathering clues from the scene of a grand ancient crime. They don't have direct witnesses, only the faint echoes of light that have traveled for millions or even billions of years. And in this particular case, the consistent location of these mysterious flashes in the spiral arms was a powerful clue, a geographical marker in the vast, featureless expanse of intergalactic space. It pointed them towards a specific type of environment, a certain kind of stellar population, and, by extension, a particular class of physical processes. The initial excitement was palpable, though expressed in the quiet, measured tones of scientific discovery. It felt like they were on the verge of cracking a code of understanding, a new dialect spoken by the most powerful explosions in the universe. The thought that LF-bots might simply be a more extreme rapid version of core collapse supernovae, fitting within an existing framework, was both intellectually satisfying and reassuring. It implied that the universe at its core might be more consistent, more predictable than these bewildering flashes initially suggested. It's a natural human tendency, isn't it? To try and fit the unknown into the known, to find comfort in familiar patterns. And for a fleeting cosmic moment, the spiral arm connection offered precisely that comfort, a gentle harbor in the vast, bewildering ocean of astronomical possibility. However, the universe, in its infinite wisdom and boundless capacity for surprise, often enjoys disrupting our neat classifications and comforting theories. Just as researchers seemed to be making solid, undeniable progress, just as they began to settle into the gentle rhythm of understanding, something happened that caught them completely off guard once more. It was a new whisper, a different kind of cosmic anomaly that gently but firmly tugged at the edges of their newfound comfort. The universe, it seemed, was not quite ready to reveal all its secrets, nor to let our theories rest easy. Just as the quiet confidence settled in, just as the spiral arm theory offered a comforting embrace, the universe, in its boundless capacity for wonder and delightful disruption, unveiled a new twist in our cosmic tale. Much like the Atlas HKO in Hawaii, which stands as a silent guardian against asteroid threats, the Zwicky Transient Facility, a remarkably wide-angle ground-based camera, continuously scans the entire northern sky. It does so with a diligent regularity, completing a full sweep every 2 days, tirelessly searching for any transient, fleeting events that might flicker into existence. In the quiet year of 2022, this patient sentinel detected yet another familiar blue explosion. It carried all the hallmarks of an LF bot. The characteristic blue emission, the intense luminosity, the rapid brightening. But then, after its initial blinding flash, this optical transient began to behave rather strangely. It was as if a cosmic dancer, having performed its grand quick flourish, suddenly decided to embark on an entirely new, unexpected routine. Instead of simply exploding once and fading away in a few days, as all the other LF bots before it had faithfully done, this particular cosmic anomaly, affectionately nicknamed the Tasmanian Devil, continued to produce short-duration bursts. And these bursts astonishingly persisted for far longer than anyone had expected. Imagine a single firework that, instead of one brilliant explosion, keeps sparking and flaring with smaller, equally intense bursts long after its initial grand display should have ended. What's more, each of these subsequent bursts seemed to be just as bright, just as luminous as the original explosion. This was, to put it mildly, very strange indeed. It was like witnessing a star that simply refused to die, a celestial phoenix that kept igniting itself moment after moment. The Tasmanian Devil, in its extended pulsating brilliance, emitted more energy than hundreds of billions of stars like our sun combined. It was a truly colossal expenditure of cosmic power, stretching out over a perplexing duration. Researchers, their minds filled with a mixture of awe and profound bewilderment, were deeply puzzled, yet again. This was truly unlike anything they had ever seen before in the long-storied history of astronomy. Now I know the skeptics among you, those with a keen eye for detail and a healthy dose of scientific caution, may be thinking, Alex, this has got to be due to some kind of technical error. A miscalibrated instrument, perhaps a fluke in quality control tests, or even a simple mathematical mistake. And indeed, the rich history of science is wonderfully instructively littered with tales of eager scientists shouting, Eureka, at supposed breakthroughs or monumental discoveries only to be gently or sometimes not so gently deflated once someone else carefully checked their workings, revealing a subtle error or an overlooked variable. It's a crucial part of the scientific process, this constant, rigorous self-correction. But this, dear friends, was not one of those moments. The data in this extraordinary case was not merely corroborated, it was enthusiastically embraced and confirmed by no less than 14 other telescopes scattered across the globe. Each one, with its unique perspective and sensitive instruments, bore witness to the Tasmanian Devil's perplexing performance. They collectively, unequivocally confirmed that this cosmic entity did in fact pulsate a minimum of 14 times. The actual total number of bursts they suspected was likely much higher, perhaps a continuous flickering dance beyond their current observational capabilities. Equally, if not more surprising, was the incredible speed of these mega-powerful pulses. They were not separated by days or hours, but often by mere minutes. Imagine the sheer raw power required for a celestial object to unleash such colossal bursts of energy, to reach peak brightness dim, and then reignite all within the space of a coffee break. It truly looked to the scientists like a star that kept dying and being revived again and again, trapped in a relentless, awe-inspiring cycle of cosmic expiration and reignition. If that truly is what the Tasmanian Devil represents, a star caught in an endless loop of cosmic rebirth, then this strange, mesmerizing phenomenon could provide brand new revolutionary insight into the very life cycle of stars. So far, our understanding of stellar life cycles has largely been built upon a collection of snapshots, like a series of still photographs, capturing different stages of a grand cosmic play. We observe a star being born another in its vibrant prime, and yet another in its dying throes. But we have never truly seen it as a continuous dynamic process, a real-time cosmic movie. The Tasmanian Devil offered the tantalizing possibility of just that, a living, breathing, endlessly repeating demonstration of a star's struggle against oblivion. In short, even though the multiple bewildering bursts of light from the Tasmanian Devil were entirely unexpected, there was still reason to suspect that these explosions in all their strange glory could have been a very unusual, perhaps extreme type of supernova. After all, none of the observations directly violated the fundamental principles of the core collapse supernova theory, merely stretched its boundaries to a bewildering new degree. It was a comfortable thought, a hopeful whisper that even this profound anomaly could eventually be understood within the established cosmic framework. The universe, in its vastness, surely held many variations on a theme, but as with all great cosmic narratives, just when we settle into a comfortable understanding, a new chapter unfolds, challenging everything we thought we knew. What came next in the quiet unfolding of cosmic events was something that truly did directly contradict the carefully constructed core collapse supernova theory. It was a data point so unexpected, so profoundly out of place, that it gently but irrevocably shattered the prevailing understanding. On a seemingly ordinary day, April 10, 2023, the patient eyes of astronomers picked up yet another magnificent, big blue explosion. It possessed all the familiar characteristics, all the telltale signs of our growing LF-bot zodiac relatives. The intense blue glow, the astonishing luminosity, the lightning-fast fade. But this particular cosmic flash, was not even close to where it was supposed to be. It was a profound geographical anomaly, a starburst in the wrong neighborhood, Unlike all the other alphabots that had gracefully obediently appeared within the swirling star-forming spiral arms of distant galaxies, this one, quickly christened the Finch, decided to make its grand solitary appearance in the most unlikely of places. It was not nestled within a vibrant galaxy. It was a staggering 3 billion light-years away from us, an almost unimaginable distance, and crucially, it was located some 15,000 light-years from the closest observable galaxy. It stood solitary in the vast empty canvas of space, a lonely beacon in the middle of nowhere. It quite literally exploded between two galaxies in the desolate, cold, and quiet intergalactic void. This was a truly devastating blow to the leading theory, the one that had provided so much comfort and seemed to tie everything together. If these powerful explosions were truly fundamentally the result of massive stars undergoing core collapse, then there was simply no way, no conceivable astrophysical scenario that such an event could be happening in the sterile, starless expanse between galaxies. Massive stars, those colossal short-lived titans, are born in the bustling nurseries of galactic spiral arms. They live fast, burn bright, and die young, never straying far from their energetic birthplaces. The Finch's location was an undeniable, glaring contradiction, a cosmic puzzle piece that simply refused to fit into the existing picture. And so, with a quiet sigh of humility, it was back to the drawing board for the researchers. The comforting, familiar map had been torn apart by this solitary, defiant flash. The universe, in its elegant complexity, had once again reminded them that its mysteries run deeper than current understanding could grasp. But this, in its own way, was also an exciting moment. When old theories shatter new avenues of exploration, new possibilities are gently revealed. It's a testament to the dynamic nature of scientific inquiry, a constant dance between what we know and the vast, beautiful expanse of what remains to be discovered. The Finch, in its cosmic solitude, had opened up an entirely new horizon of questions, inviting astronomers to dream bigger, to imagine the impossible, and to humbly search for entirely new explanations for its blinding, lonely light. It was a gentle reset, a quiet invitation to reconsider the fundamental forces that might be at play in the farthest reaches of the cosmos. With the established narrative of core collapse supernovae utterly broken, by the lonely brilliance of the Finch researchers, found themselves gently ushered back to the drawing board. It was a humbling yet exhilarating moment, a blank slate where old assumptions could be set aside and fresh, bold ideas could begin to unfurl. They carefully considered what could possibly have caused the Finch to explode in such an desolate, star-forsaken location. Out of this thoughtful contemplation, two compelling yet still speculative new theories began to emerge, each attempting to weave a coherent story around this solitary cosmic enigma. The first theory gently suggested that the Finch could be the dramatic result of stars being torn apart by an intermediate mass black hole, IMBH. Imagine, if you will, a cosmic entity that sits uncomfortably yet fascinatingly in the middle of our understanding of black holes. We know with a comforting certainty about their smaller relatives, the stellar mass black holes born from the spectacular collapse of giant stars, typically with masses just a few times that of our Sun. And we are quite familiar with their colossal domineering cousins, the supermassive black holes, those gargantuan behemoths, lurking at the hearts of nearly every galaxy, boasting masses millions or even billions of times greater than our Sun. These cosmic titans, both the tiny and the grand, have been confirmed to actually exist, their gravitational signatures echoing throughout the cosmos. But this middle child, this intermediate mass black hole, remains purely theoretical, a whispered possibility in the grand symphony of the universe. Its existence, though widely anticipated by some models, has never been definitively proven. Yet if they did exist, if these enigmatic entities possessing masses 100 to 10,000 times greater than our Sun were indeed out there, could they be the unseen orchestrators behind this elusive blinding light show, particularly in such a desolate place? The idea is tantalizing, Astronomers, with their sophisticated tools of simulation, have painted vivid, intricate pictures of how such a cosmic drama might unfold. In these digital realms, they've shown that stars can orbit intermediate mass black holes, not just once, but as many as 5 times, spiraling ever closer before finally being violently ejected. With each agonizing orbit around the black hole, the star is effectively being ripped apart by immense tidal forces, losing more and more of its mass, like a celestial onion being peeled, layer by agonizing layer. This process is known as a tidal disruption event, a violent luminous spectacle. Finally, after enduring this harrowing cosmic dance, the remaining stellar matter, a mere shredded remnant, would be flung back out into the galaxy, or in the case of the Finch, perhaps into the lonely intergalactic void at truly astonishing speeds, as high as 10% the speed of light. Imagine the sheer raw power required to accelerate matter to such incredible velocities. This kind of event, with its rapid violent destruction and the immense energy released, would be entirely consistent with the observed speed and the blinding brightness of LF bots, lending a quiet, hopeful weight to this intriguing, albeit unproven theory. The next question, of course, gently arises: if these intermediate mass black holes truly exist, where would we most likely find them? Where might these theoretical cosmic architects hide? One of the most likely places researchers would expect to find intermediate mass black holes is within globular star clusters. Picture these as dense, ancient spherical collections of hundreds of thousands, sometimes millions of stars, all bound together by gravity. These clusters are often found in a galaxy's outer halo, that vast, sprawling, and somewhat ethereal region that extends far beyond the main disk and central bulge of a galaxy. Galaxies have these halos like a shimmering, almost invisible aura stretching far into the surrounding space. They are most visibly prominent in spiral galaxies like our own familiar Milky Way. In our cosmic home, the outer halo stretches an impressive 1 million light-years from its galactic center, a truly immense, sparsely populated realm. Some thoughtful scientists have mused that it is entirely possible that the Finch, this solitary burst of light, could have been located inside just such a globular star cluster, one that happened to be situated far out in the intergalactic medium, adrift between galaxies. If this were indeed the case, and if intermediate mass black holes truly do exist within these ancient stellar congregations, then it could be entirely plausible that the Finch, in all its perplexing glory, was caused by one of these unusually sized black holes brutally tearing apart a large, unsuspecting star. It's a compelling narrative, one that would explain the immense energy, the rapid onset, and crucially the baffling location of this cosmic enigma. It paints a picture of violent, unseen forces at play in the most desolate corners of the universe, a silent, powerful drama unfolding far from the bustling galactic cities. The second theory, equally captivating and dramatic, that researchers put forward to explain the Finch's lonely explosion, suggested a different kind of cosmic embrace, that it could have been the result of 2 neutron stars moving towards each other in increasingly tight spirals until they finally collided. Imagine 2 incredibly dense, unimaginably heavy remnants of dead stars, each packing more mass than our sun into a sphere no larger than a city locked in a gravitational dance. As they draw closer, their orbits accelerate, spiraling faster and faster, until with a cataclysmic final embrace, they merge. This kind of event, a kilonova, is known to be one of the biggest, most energetic stellar blasts in the universe, an explosion that truly shakes the fabric of spacetime. One telltale sign of a kilonova, a unique cosmic fingerprint, is the presence of gravitational waves. These ripples in spacetime, predicted by Einstein, come through to our instruments as a hallmark chirp. Imagine a faint rising tone gradually increasing in frequency as 2 massive objects spin around each other with ever-increasing speed until they finally collide and merge in a spectacular cosmic crescendo. If we could find such a chirp When meticulously analyzing the data from the Finch, it would lend incredibly strong credence to this neutron star collision theory, providing a direct physical link to such a cataclysmic event. It would be a smoking gun, a clear signature of the universe's most violent dances. However, as bad luck would have it, in the grand unpredictable ballet of cosmic observations, our most sensitive chirp detector, the Laser Interferometer Gravitational Wave Observatory, or LIGO, was unfortunately down for maintenance at the precise time the Finch occurred. Imagine waiting for a rare cosmic performance only to find the concert hall dark. This crucial timing meant that we simply don't know if such gravitational waves were indeed emitted during the Finch's explosion, as we have no data on them. The universe, it seems, can sometimes be a cruel mistress, withholding the very clues we most desperately seek. Beyond the absence of gravitational wave data, there was another subtle, yet nagging piece of the puzzle. One thing we do know is that no gamma-ray burst was detected in conjunction with the Finch. This is something you might typically expect to see with a kilonova of this immense size, a powerful high-energy flash accompanying the collision. However, we must remember the incredible distances involved. This explosion happened a staggering 3 billion light-years away. That's really profoundly far. Perhaps too far for whatever faint gamma-ray data there might have been to be reliably detected by our instruments here on Earth, diluted and stretched across such an immense cosmic canvas. The vastness of space, while awe-inspiring, can also be a formidable veil obscuring crucial information. All in all, the data, or rather the lack of conclusive data, in certain key areas means that none of this information can conclusively confirm or definitively reject the neutron star collision theory for the Finch. It's an incredibly frustrating position for an astronomer, isn't it? To bear witness to such an incredibly rare, new, and undeniably powerful phenomenon, a fleeting glimpse into the universe's most violent heart, and yet not possess the full suite of data to conclusively understand what is truly causing it. It's like being shown a single breathtaking frame from an epic movie without the context of the rest of the film. I guess patience, that quiet, unwavering virtue, is an incredibly underrated quality for an astronomer to possess a constant companion on their long, often unrewarded vigil. But these dedicated cosmic explorers are not simply sitting on their hands patiently, waiting for the universe to reveal its secrets at its own leisurely pace. No, their minds are already ablaze with ingenious plans, meticulously charting the next steps in their relentless quest for understanding. Scientists are already planning to ingeniously use the exquisite optics and unparalleled sensitivity of the James Webb Space Telescope to carry out a meticulous search for any faint, hidden globular clusters in the exact cosmic location as the Finch. If they can indeed pinpoint such a cluster, it would lend immense support to the intermediate mass black hole theory, gently clarifying if they are on the right path with this intriguing, albeit still unproven, explanation. It would be like finding a hidden village in the vast empty desert, a potential home for the theoretical cosmic shredders. In the meantime, other researchers are focused on a different, yet equally vital strategy, tirelessly broadening the sample size. The more LF bots we can detect, the more of these fleeting blue whispers we can capture, the more intimately we will learn about them. The 6 or so we have seen so far have certainly taught us some profound and perplexing things, but we still have an immense amount left to learn. Vast stretches of the LF bot mystery still shrouded in cosmic fog. The only way we're truly going to get a larger sample, a more comprehensive understanding, is to keep sweeping the sky with wide-field surveys. Those tireless celestial sentinels, like the Atlas HKO, and the Zwicky Transient Facility, ever vigilant for the next unexpected flash. And the future holds even greater promise for this relentless cosmic hunt. Scientists' hopes are currently pinned on the Vera C. Rubin Observatory, a colossal instrument currently under meticulous construction in the high, dry air of Chile. This revolutionary telescope, a true marvel of engineering, is designed to scan the entire southern sky every few nights, a breathtaking feat of observational power. It is expected to be fully operational by 2025, and, with its unparalleled light-gathering capabilities, will be able to capture an astonishing 10 times more light than all previous facilities combined. Imagine a cosmic net cast wider and deeper than ever before, ready to ensnare these elusive flashes. Following these initial detections, meticulous follow-up observations with powerful instruments like the Hubble Space Telescope, along with an array of ground-based telescopes, will help to meticulously analyze even more intricate information, which could in turn lead to even more profound breakthroughs, gently unraveling the very fabric of these cosmic enigmas. LFBOTs are undoubtedly a super new phenomenon, a fresh chapter in the cosmic story that we still don't fully understand. Scientists themselves, with a refreshing humility, openly admit that the discovery of the Finch in its profound solitude raises more questions than it answers. The more we learn about these bright blue explosions, these fleeting luminous whispers from the deep cosmos, the more they continue to surprise us, to challenge our assumptions, and to expand the very horizons of our cosmic imagination. All there is left to do then is what hundreds of generations of astronomers have done for centuries before us: point our telescopes up to the sky watch with patient, unwavering curiosity, and simply humbly wait for the universe to whisper its next secret. Let us now gently pivot from the bewildering blue flashes of the LFBOTs and turn our attention to another profound, yet almost imperceptible, cosmic phenomenon: gravitational waves. These are whispers from the very fabric of space-time itself, ripples that travel across the universe, carrying tales of its most violent and magnificent events. Albert Einstein, in his profound general theory of relativity, first predicted their existence over a century ago. Yet even he, in his unparalleled brilliance, was quite pessimistic about our chances of ever detecting them. He thought these cosmic disturbances would be so incredibly small, so infinitesimally faint, that they would forever escape our ability to measure them. And who could truly blame him? The changes in distance that our instruments seek to measure are often a mere 1/10,000th the length of a proton. Yes, you heard that correctly. 100,000 times smaller than a single proton, that fundamental building block of matter. Imagine the almost unimaginable precision required to sense such a minuscule tremor. Yet despite Einstein's gentle skepticism and the mind-bending scale of the challenge, humanity, with its insatiable curiosity and ingenious spirit, achieved the impossible. On September 14, 2015, in a quiet triumph of human ingenuity, scientists at the Laser Interferometer Gravitational Wave Observatory LIGO detected gravitational waves directly for the very first time. It was a stunning achievement, a profound moment that justly led to the 2017 Nobel Prize in Physics. Why was this so significant, you might ask? Beyond the mere confirmation of a scientific prediction, let's imagine an analogy, a gentle thought experiment, to grasp the true magnificence of this achievement. Picture humanity evolving for thousands of years without the ability to see light. We would live in a world of touch, sound, smell, and taste, fumbling in the dark, relying solely on our other senses to navigate reality. Then one day someone invents a machine that can suddenly perceive light for us. In time, through this new sense, we would begin to see everything from the delicate tips of our own noses to the farthest flung, most ancient galaxies shimmering in the cosmic distance. This analogy, I believe, beautifully captures the profound impact of LIGO. It's about much more than simply proving a scientific prediction. LIGO enables us to perceive the physical universe, to grasp the very nature of reality on an entirely new level, adding an entirely new dimension to our cosmic senses, like photons, the tiny packets of light that grace our eyes. Gravitational waves also travel at the speed of light. As they ripple across the boundless expanse of space-time, their faint oscillating signals are all around us, unseen, unheard, yet ever present. By meticulously listening for these gravitational waves with some of the most sensitive instruments ever built by human hands, Scientists are now able to record the almost imperceptible tremors of distant, incredibly violent cosmic events. They are picking up the echoes of black holes forming, of supernovae exploding, and perhaps most tantalizingly, of exotic phenomena we haven't even begun to discover or imagine yet. So what exactly are these mysterious gravitational waves? What colossal cosmic ballet causes them to ripple across the universe? And why is LIGO's extraordinary ability to detect them already transforming our understanding of the universe and indeed of reality itself? Let us gently explore these profound questions. Gravitational waves are one of the stranger yet most elegant implications of Albert Einstein's general theory of relativity. As we've softly explored before, spacetime is a remarkable model that combines the three familiar dimensions of space length, width, and depth, with the fourth dimension of time, weaving them into a single seamless fabric, a cosmic manifold. All objects with mass, even the smallest pebble or the most colossal galaxy, create a subtle curvature, a gentle dimple in this fabric of spacetime. And quite intuitively, objects with a lot of mass create a lot of curvature, a deeper, more profound dimple, which we as inhabitants of this universe experience as the pervasive force of gravity. A simple calming way to visualize this abstract concept is to imagine a taut elastic surface like a trampoline stretched perfectly flat. Now gently place a small pool ball onto that surface. It will create a slight indentation, a gentle curve. Now next to it, place a much more massive bowling ball onto that same elastic surface. You'll immediately notice the deeper, more pronounced curvature it creates. The more massive bowling ball, quite simply, will warp the fabric of the surface much more significantly. This analogy beautifully illustrates how mass warps space-time, creating the very hills and valleys that guide the motion of everything in the universe. As objects move across this curved space-time, that curvature, that dimple changes position with them, trailing like a shadow. One of the truly amazing consequences of this intricate dance is that when objects of a certain immense mass accelerate, when they undergo rapid violent changes in their motion, they can send tiny ripples, like pebbles dropped into a cosmic pond, across the very fabric of spacetime itself. These ripples carry gravitational energy outward, while this requires a very special, very cataclysmic set of conditions, namely incredibly massive objects undergoing incredibly rapid acceleration, like merging black holes or colliding neutron stars. Such a momentous event would send these ripples, these gravitational waves, propagating outward at the speed of light in all directions, gently yet powerfully carrying their cosmic message. Think of them, if you will, like the familiar ripples on a calm pond after a stone has been tossed in. But instead of traveling through water, these profound disturbances travel through the very fabric of space-time itself. And just as in the pond analogy, these disturbances, these cosmic waves become weaker, more subtle as they radiate outward, spreading their energy across ever-increasing distances. To a distant observer like us here on Earth, the distance between objects would appear to subtly expand and shrink ever so slightly as the gravitational wave gently passes through. It's a truly mind-boggling concept to imagine, isn't it? The very fabric of reality, seemingly breathing, expanding, and contracting with the passage of these unseen waves. Yet despite Einstein's brilliant prediction of the existence of gravitational waves, as mentioned, he remained gently pessimistic about our chances of ever detecting them. He believed that these space-time disturbances would be so incredibly so infinitesimally small that they would forever escape our most sensitive instruments. And given the scale, his skepticism was entirely understandable. Many of the changes in distance that LIGO tirelessly seeks to measure are indeed incredibly tiny, often just 1/10,000th the length of a proton. Imagine trying to measure a change in distance equivalent to shifting a mountain range by the width of a human hair. That is the incredible precision we are talking about. And yet, these incredibly faint signals, these subtle whispers from the depths of the cosmos, come encoded with all kinds of profound information about their origins. They carry within them the story of when they originated, how far they traveled across the vast expanding universe, and most crucially, what kind of cataclysmic event produced them. It's like receiving a highly compressed, incredibly detailed message from the very beginning of time carried on the faintest of ripples. This is precisely where LIGO, that marvel of human engineering, quietly steps onto the cosmic stage. LIGO is not one but two observatories strategically located in Hanford, Washington and Livingston, Louisiana, across the vast expanse of the United States. It is primarily funded by the United States National Science Foundation and meticulously operated by the brilliant minds at MIT and Caltech. Among its driving forces, its guiding lights are the renowned physicists Kip Thorne, Rainer Weiss, and Barry Barish, all of whom, in a well-deserved recognition of their groundbreaking work, shared the 2017 Nobel Prize for their decisive contributions to the direct detection of gravitational waves. At its heart, LIGO is essentially a very large-scale and incredibly sensitive interferometer, an ingenious invention that has actually been around since the 1880s. An interferometer, in its simplest form, meticulously measures what happens when light waves are precisely combined from two or more distinct sources. For example, you could use an interferometer to test whether light travels at different speeds through different substances, such as through air versus through water. Even a subtle, tiny difference in speed, a mere fractional change, will produce a distinct interference pattern when the light waves combine. This is much like what happens when two ripples on a pond gently intersect. If the peak of one ripple precisely hits the valley of a second ripple, they will subtract from each other, canceling each other out and producing a flat, undisturbed surface. However, if the peaks line up exactly, if the waves are perfectly in phase, it means they add to each other, creating a larger, more pronounced wave. This is essentially what the interferometer measures with light, by precisely observing how in or out of phase two light waves are when they recombine. An observer can infer the relative speed and thus any subtle changes in the path length of those waves. And crucially, the larger and more powerful the interferometer, the more incredibly sensitive it becomes to even the most minute of changes, making it capable of detecting those proton-sized ripples in spacetime. Here's how this intricate cosmic listener quietly works its magic. Each of LIGO's two observatories continuously fires a powerful laser at a beam splitter, a precisely angled mirror positioned at a 45-degree angle. This laser beam itself is formidable, operating at around 750 kilowatts. Powerful enough, one might imagine, to vaporize you completely if you were to somehow wander into its path. The beam splitter then, with exquisite precision, divides this single powerful laser beam into two separate beams, sending them perpendicularly down two long vacuum-sealed arms. Each of these arms stretches a remarkable 4 kilometers in length, forming an enormous L shape. At the very end of each arm, there is a highly polished mirror. The beams then don't just hit the mirror once. They are designed to bounce back and forth between this end mirror and a recycling mirror at the other end nearly 300 times. This ingenious design effectively increases the optical distance that the light travels from a mere 4 kilometers to an astounding 1,200 kilometers within each arm. Remember what we said with interferometers: bigger is truly better, as the longer the path, the more sensitive the instrument to minute changes. After completing their nearly 300 round trips, their long, precise journeys down their respective arms, the two laser beams gracefully combine again at the beam splitter, having traveled identical effective distances in a perfectly still universe. From there, the recombined light heads towards a photodiode, which is a highly light-sensitive semiconductor, essentially a detector that converts light into an electrical signal. In a perfectly undisturbed world, if no gravitational wave were to pass through, the two beams would arrive at the photodiode precisely in phase. This means their frequencies would perfectly subtract each other, like two perfectly aligned opposing waves, resulting in no light, or virtually no light, arriving at the photodiode. It would be a moment of perfect engineered silence. But if a gravitational wave, however faint, were to pass through the observatory, it would subtly, imperceptibly stretch and squeeze space-time. This tiny transient distortion would cause the distance each laser beam travels to be infinitesimally, yet crucially different. One arm might momentarily lengthen by a fraction of a proton's width, while the other shortens by an equally tiny amount. This minute differential in path length would cause the two laser beams to arrive at the photodiode ever so slightly out of phase. And when they recombine out of phase, their frequencies no longer perfectly cancel. The photodiode would then pick up a tiny faint signal, a delicate flicker of light, indicating the unmistakable presence of a gravitational wave. It is an extraordinary testament to human ingenuity, capturing the universe's most subtle whispers through the precise interference of light. Now this description, this elegant ballet of light and mirrors, is how LIGO works in a perfect world, a pristine, idealized cosmic laboratory. But in the messy, wonderful reality of our universe and our planet, the interferometer is constantly picking up noise. Imagine trying to hear the faint flutter of a butterfly's wings in the middle of a bustling city. Every tremor, every distant rumble, every microscopic vibration on Earth can mimic the incredibly subtle signal of a gravitational wave. To minimize this overwhelming symphony of terrestrial noise, LIGO employs incredibly smooth, precisely engineered 40-kilogram mirrors each, a masterpiece of optical perfection suspended by the finest, strongest silica threads. These mirrors are so perfectly crafted that if you were to magnify one to the size of a continent, the largest imperfection would be no bigger than a single atom. They hang like delicate pendulums isolated from the slightest tremble. Any stray particles, even a single dust motes lingering in the interferometer arms, are also a profound problem. Imagine a tiny speck in the path of a laser beam trying to measure changes smaller than an atom. This is why LIGO goes to extraordinary lengths, meticulously pumping nearly all the air from its vacuum chambers, reducing the pressure to an astonishing 1/trillionth of atmospheric pressure. It's an almost perfect vacuum, a silent empty highway for light, minimizing any interference from residual gas molecules. But even with such meticulous engineering and near-perfect vacuums, there's another deeper problem at these minuscule levels. A challenge that delves into the very heart of reality. Even quantum mechanics becomes a nuisance. Quantum mechanics, as we gently know, describes the behavior of matter and energy at the atomic and subatomic scales, where the rules of our everyday world gracefully give way to a realm of inherent randomness and uncertainty. At LIGO's extreme sensitivity, this quantum randomness, this fundamental fuzziness of the universe, can introduce subtle inherent noise into the behavior of the photons themselves. Those tiny packets of light that make up the laser beam. It's like trying to draw a perfectly straight line with a pencil that subtly jiggles on its own. LIGO, however, mitigates this fundamental quantum noise with an ingenious technique involving an optical cavity, which essentially squeezes the light. Imagine, if you will, that light has two fundamental properties: its phase, the precise alignment of its waves, and its amplitude, the height or intensity of its waves. Quantum mechanics dictates that you can't perfectly know both with absolute certainty at the same time. Knowing one precisely makes the other more uncertain. By squeezing the light, LIGO deliberately minimizes the light's phase noise, the kind of noise that would directly interfere with the path length measurement, and in doing so, it effectively squeezes that inherent quantum uncertainty into amplitude noise. This amplitude noise, manifesting as subtle random fluctuations in the brightness of the laser, is something the interferometer doesn't directly measure for its primary signal. In other words, the quantum randomness, that fundamental jitter, will show up more in the height of the waves, which is less critical, rather than in their timing or phase, which is crucial for detecting gravitational waves. Quantum randomness, you see, is a fundamental fact of life. It simply cannot be eliminated entirely. But through such clever design, It can be artfully shifted much as you might gently move clutter from your bedroom floor into a closet. The chaos isn't gone, no, but it's out of sight for the moment, placed where it won't interfere with the delicate measurement. Plus, the ultimate goal isn't to eliminate noise completely, which is an impossible dream, but to achieve the best possible signal-to-noise ratio, allowing the faint whisper of a gravitational wave to rise above the inherent cosmic hum. So this has been a pretty good overview of how LIGO, in all its intricate, precise glory, quietly works to listen for the universe's deepest tremors. What, then, has this extraordinary instrument discovered? Since it began its cosmic vigil, as I mentioned earlier, LIGO detected its very first signal, its inaugural cosmic whisper, in 2015. This groundbreaking event was named GW1579. Scientists meticulously studied the data sifting through the faint complex echoes, and through this painstaking analysis, they learned that this momentous signal was caused by the unimaginably powerful merger of two black holes, a cosmic dance culminating in a singular cataclysmic embrace that occurred approximately 1.6 billion light-years away from us. Imagine light and gravitational ripples traveling for an astonishing 1.6 billion years, carrying the tale of this ancient violent union across the expanding universe, only to finally reach our eager detectors. These two black holes, one a colossal 29 times the mass of our Sun, and the other a slightly smaller but still mighty 36 solar masses, became what is known as a binary system. They spiraled around each other gracefully, yet with immense accelerating speed, drawing ever closer until they finally merged into a single, even more colossal black hole. In the final breathtaking 20 milliseconds of this cosmic embrace, they released a blast of pure energy that was so incredibly powerful that now get ready for this number. Because this is what the scientists actually humbly think, it contained 50 times the combined light power of every single star in the observable universe. At the risk of sounding somewhat crude or overly dramatic, that, my dear listeners, is utterly nuts. I've read this astonishing fact many times over, and yet even now I still struggle to truly comprehend what it means. Imagine a single event lasting less time than a blink, unleashing more energy than the combined brilliance of quadrillions upon quadrillions of suns. It's a number that defies human intuition, a scale of power that stretches the very limits of our imagination. Yet, after traveling for that staggering 1.6 billion years across the vast silent expanse of the cosmos, the disturbance, the actual ripple in space-time that reached LIGO, was so incredibly faint that it moved LIGO's massive 4-kilometer arms by a mere 1,000th of the width of a proton. To truly visualize this almost unimaginable level of precision, imagine the immense distance between us and Proxima Centauri, our nearest stellar neighbor beyond the Sun, which is roughly 4.2 light-years away. Now picture that immense distance shrinking or expanding by the delicate width of a single human hair. That, in essence, is the level of almost miraculous precision that LIGO was able to detect. If that isn't one of the most astonishing feats in human history, a testament to our relentless pursuit of knowledge and our boundless capacity for ingenuity, then I honestly don't know what is. It's a quiet marvel, a profound validation of our ability to listen to the faintest whispers of the universe. And this, mind you, was just the very first gravitational wave that LIGO so magnificently detected. The second detection, another soft cosmic tremor, occurred a mere 3 months later in December 2015. That signal also carried the telltale signature of a black hole merger, a violent distant embrace that took place approximately 1.4 billion light-years away. Over its initial 3 meticulous observation runs, LIGO, with its ever-improving sensitivity, remarkably recorded more than 80 black hole mergers, each one a unique story of cosmic violence and transformation, adding to our growing cosmic symphony of gravitational echoes. But perhaps one of the most exciting and groundbreaking detections occurred in August 2017. This time, LIGO detected not a black hole merger, but the merger of two neutron stars. This truly monumental event, designated GW170817, was notable for a profoundly important reason. It was the very first gravitational wave event to be corroborated, to be confirmed and amplified by simultaneous electromagnetic observations from an astonishing 70 observatories scattered across our planet. This was a true breakthrough, not only in the burgeoning field of gravitational wave detection, but crucially in the new and revolutionary discipline of multi-messenger astronomy. Multi-messenger astronomy. My dear listeners, is like suddenly gaining a multitude of new senses to perceive the cosmos. Before this, we largely relied on electromagnetic radiation, light radio waves, X-rays, gamma rays to understand the universe. But with the addition of gravitational waves and potentially neutrinos, we are now able to perceive the universe through entirely new channels, like hearing and feeling the cosmic symphony, not just seeing it. This event, GW170817, marked a pivotal moment, allowing us to combine the sound of space-time rippling with the sight of light, painting a far richer, more complete picture of a single cosmic event. It turns out this initial success was just LIGO warming up a gentle prelude to even grander discoveries. During these initial 3 observation runs, LIGO meticulously collected a treasure trove of data, slowly building a new narrative of cosmic violence and rebirth. But the journey of discovery, like the universe itself, is an ongoing, evolving process. As of May 2023, LIGO has embarked on its 4th observation run, a new chapter in its cosmic listening, equipped with even better sensitivity than ever before. This remarkable improvement comes after its latest round of meticulously planned upgrades, which kept LIGO offline for 3 years, a quiet period of intense refinement and re-engineering. The observatories now boast even more reflective mirrors, suspended with even greater precision and feature-improved light-squeezing techniques, leading to even lower quantum uncertainty. Imagine a cosmic ear, now even more finely tuned, capable of catching the faintest whispers from the distant past. And in this new chapter of cosmic listening, LIGO also has the crucial support of KAGRA, a brand new interferometer observatory nestled deep in Haida, Japan. KAGRA is truly unique, located entirely underground, making it the world's very first subterranean gravitational wave observatory. This subterranean placement provides unparalleled isolation from terrestrial seismic noise, making it incredibly sensitive. It is also the first to ingeniously use cryogenic mirrors, cooled to incredibly low temperatures to further reduce thermal noise, allowing for an even purer, clearer signal. This global network of gravitational wave detectors working in concert is slowly, patiently painting an ever more detailed picture of the universe's most violent and elusive events. The early results from this 4th run are already incredibly promising. During an engineering run on May 18th, LIGO scientists whispered that they had already received a signal that was possibly caused by a neutron star being swallowed by a black hole. Imagine the profound violence and transformation of such an event, a cosmic feast of unimaginable scale. We'll have to wait a while for meticulous confirmation, of course, as scientific rigor demands patience and verification. But if these early results are any indication, LIGO in its renewed and enhanced glory is about to blow the doors off our understanding of gravitational wave-generating phenomena, opening up a torrent of new insights into the universe's most dramatic dances. So what other developments, what other cosmic horizons lie ahead for our patient gravitational wave listeners? The journey, it seems, is only just beginning, with new instruments and collaborations constantly emerging. India, for instance, is diligently preparing a collaborative project called LIGO India, or Indigo. This ambitious undertaking will create a 3rd large-scale gravitational wave detector, strategically placed on a different part of the globe. Why is this significant? Because having at least 3 widely separated detection sites is crucial for triangulating the precise location of a gravitational wave source in the vast 3-dimensional expanse of the cosmos. Imagine trying to pinpoint a distant lightning strike with only one ear. It's much easier with two, and even better with three, allowing for far more accurate celestial mapping. LIGO India will help our global network of observatories pinpoint exactly where these cosmic tremors are originating, from adding another layer of detail to their profound stories. Looking further into the future, a more distant but equally exciting upgrade is planned for LIGO itself. Around 2027 to 2028, LIGO will implement its LIGO Voyager upgrade. This next generation of enhancements aims to achieve even higher sensitivity, pushing the boundaries of what's detectable. It will feature 4 times heavier mirrors, which counterintuitively perhaps will allow for even more precise measurements by reducing the impact of quantum noise. It will also incorporate higher frequency lasers, providing a finer, more detailed probe of spacetime's subtle undulations. Each technological leap, each meticulous refinement, brings us closer to hearing the faintest, most ancient whispers from the universe's beginning. And in the more distant future, a truly monumental third-generation facility has been proposed, a grand vision known as Cosmic Explorer. This ambitious project would feature 2 entirely new observatories, colossal in scale with arms spanning an astonishing 40 kilometers and 20 kilometers respectively. Remember, with interferometers, the guiding principle is beautifully simple. Bigger is always better. The longer the arms, the greater the distance the light travels, and thus, the more sensitive the instrument becomes to the almost infinitesimal stretching and squeezing of spacetime caused by gravitational waves. Cosmic Explorer promises to be a behemoth, a colossal ear capable of listening to a far greater volume of the universe, reaching deeper into cosmic time than ever before. But the proposal that truly ignites the imagination, the one that makes the heart of a cosmic explorer flutter with anticipation, is the Laser Interferometer Space Antenna, or LISA. This would be an unprecedented leap, the very first space-based gravitational wave observatory. Imagine 3 spacecraft gracefully flying in a precise triangular formation, separated by an astounding 2.5 million kilometers. Within this vast cosmic triangle, lasers would continuously beam between the spacecraft, creating an interferometer of truly astronomical proportions. This space-based interferometer, liberated from the incessant terrestrial noise and seismic rumblings of Earth, would be so incredibly immense and so exquisitely precise that scientists quietly hope it would be adept at uncovering even more exotic and theoretical sources of gravitational waves. These could include the echoes of cosmic strings, hypothetical defects in the fabric of spacetime itself, and other speculative phenomena that remain purely in the realm of theoretical physics. In theory, if LISA fulfills its promise, it could help us stare directly into the very fabric of reality, observing phenomena that are currently beyond our wildest dreams. With a planned launch date of 2037, we're still over a decade away, a blink in cosmic time, but it's never too early to start counting the years, to let our minds drift into the possibilities that such a profound instrument might unveil. So there you have it, a journey through the intricate world of LIGO, and a glimpse into how scientists are using these subtle yet powerful gravitational waves to better understand the universe. These waves give us direct, undeniable evidence of incredibly remote and ancient phenomena, events that simply cannot be measured or even perceived by any other means. They are a new window, a completely fresh perspective on the most violent and energetic processes in the cosmos. And beyond that, they can serve as a secondary, incredibly powerful way to measure observations already made by other instruments, like the James Webb Space Telescope or Hubble, providing a complementary reinforcing layer of understanding. In time, this revolutionary field, this new cosmic sense, should allow us to understand the very nature of our universe, its tumultuous history, and perhaps even its grand unfolding future with a clarity and depth previously unimaginable. I hope you found this episode as fascinating, as mind-expanding as I have in describing it. The universe, it seems, is always full of new sounds, new sights waiting for us to simply learn how to listen and how to see. Now let's gently shift our gaze from the rhythmic dance of gravitational waves to another type of cosmic explosion, one that speaks in a blinding flash of high-energy light. In October 2022, a brilliant, terrifying flash pierced the cosmos. It was brighter and more intensely powerful than anything human civilization had ever witnessed before. And that, my dear listener, is not an exaggeration. The sheer raw strength of this blast momentarily blinded our most sensitive gamma-ray detectors across the entire world, utterly saturating their sensors with its overwhelming brilliance. In a matter of mere seconds, it unleashed more energy than our sun, that patient life-giving star, will emit over its entire staggering 9 billion-year lifespan. For the 18 months that followed this unprecedented event became the most widely studied gamma-ray burst, GRB, in history, a subject of intense scientific scrutiny and profound wonder. It was creatively, yet aptly dubbed, the boat, standing for the brightest of all time. As researchers, with their characteristic patience and meticulousness, began to decipher its cause, their findings gently unraveled one mystery after another, leading them down unexpected paths of discovery. Scientists for decades have been diligently cataloging gamma-ray bursts, these brief, intense flashes of high-energy gamma radiation, which can last anywhere from mere milliseconds to several minutes. The very first of its kind was detected quite by accident in 1967. Back then, American satellites, originally designed with a far more terrestrial purpose, namely, detecting covert Soviet nuclear testing, picked up an unusual and profoundly mysterious pattern of electromagnetic energy. Since that serendipitous discovery, gamma-ray bursts have become a source of tremendous interest, a captivating enigma for the cosmological community. They are, in essence, cosmic laboratories, allowing scientists to study states of matter and physics that are simply not reproducible here on Earth. Imagine conditions of unimaginable density and energy far beyond anything we can create in our most advanced laboratories. Essentially, GRBs provide researchers with a fleeting but profound glimpse into how stars are formed and how they evolve across the entire vast timeline of the universe, from its earliest moments to the present day. There are, broadly speaking, two different kinds of gamma-ray bursts, each telling a slightly different yet equally dramatic cosmic story. Short gamma-ray bursts are, as their name suggests, incredibly brief, typically lasting less than 2 seconds. These ephemeral flashes are generally attributed to either the cataclysmic collision of two incredibly dense neutron stars, the collapsed super-heavy remnants of massive stars, or the equally violent merger of a neutron star and a black hole. These events are often followed by a kilonova, an emission of bright light that results from the radioactive decay of newly formed chemical elements, a glowing aftermath. This rapid decay, this brief burst of light, is crucial because it creates even heavier elements, those precious components that make up much of the world around us. This process is an important feature of kilonova, and we'll gently discuss its significance later. Anything lasting longer than 2 seconds, on the other hand, is classed as a long gamma-ray burst. These prolonged, powerful flashes are thought to be caused by the explosive, majestic deaths of truly massive stars, those colossal giants that far exceed the size of our sun, and their subsequent equally spectacular supernova explosions. In these scenarios, the star's collapsing core may form either a new neutron star or, more often, a nascent black hole. These long GRBs typically occur in regions characterized by low metallicity, meaning they formed when there were fewer heavy elements present in the universe, as heavy elements are created over time by generations of stars. This often means we observe them originating from very distant parts of the observable universe, because we are essentially looking back in time to an era when the universe was much younger and less chemically enriched. When we witness one of these, we are truly witnessing events from billions of years ago, echoes from a younger, more pristine cosmos. In the case of both long and short gamma-ray bursts, the newly formed black hole, or sometimes a spinning neutron star, blasts out incredibly powerful jets in opposing directions. Imagine two incredibly narrow-focused beams of pure energy and particles shooting out from the poles of the collapsing star. These jets contain particles accelerated to speeds incredibly close to the speed of light, almost touching the cosmic speed limit. When these superfast particles interact with the surrounding interstellar matter, the gas and dust in the star's vicinity, they emit the very gamma rays that our distant detectors here on Earth are able to pick up, carrying the story of the star's dramatic final moments across unimaginable distances. So what exactly made the boat, this record-breaking GRB 221009A, so incredibly special, so profoundly unique that it continues to captivate the minds of astronomers? Let's begin by gently analyzing some of its key perplexing characteristics. Firstly, the boat was not a fleeting whisper. It lasted an astonishing 10 whole minutes, and its energetic aftermath, its lingering glow, was detectable for a remarkable 10 hours after the initial blinding flash. This longevity, combined with its sheer power, was already a strong hint at its unprecedented nature, but perhaps the most striking characteristic was its proximity, relatively speaking, in the cosmic neighborhood. It occurred in the familiar constellation of Sagitta, a mere 2 billion light-years away. While 2 billion light-years is an immense distance by human standards, it is significantly, wonderfully closer than most other gamma-ray bursts we have detected until now. Most GRBs, as we've noted, are incredibly distant, originating from the earliest epochs of the universe. In fact, such a blindingly bright explosion occurring so relatively close to Earth is thought to be a truly rare event, perhaps a 1 in 10 thousand-year occurrence. Imagine the last time a burst of this magnitude, at this proximity, graced our skies. Early humans had barely begun to experiment with farming. It was a cosmic event that truly transcended human history. As is the case with other long gamma-ray bursts, scientists quickly concluded that a collapsing and exploding massive star, a collapsar, was undoubtedly behind this colossal event. The sheer duration of the burst was a clear signature of a long GRB. But this is where things began to get fuzzy, where the familiar narrative started to unravel. A supernova explosion alone, even a very powerful one, simply isn't enough to explain the truly mind-boggling magnitude of the gamma rays emitted by the boat. This was not just a bright flash. The boat was a whopping 70 times stronger than any other gamma-ray burst ever detected before it. Imagine turning up the volume on a cosmic amplifier to an unprecedented, deafening level. Initially, the most straightforward theory, the comforting explanation was that this must have been the supernova of an absolutely gigantic, unheard-of star, a cosmic leviathan, the likes of which we rarely, if ever, see. But upon closer, more meticulous inspection of the afterglow, the lingering fading light that followed the initial burst, scientists discovered something utterly perplexing. The supernova behind the boat, the dying star that birthed this colossal flash, was shockingly quite ordinary. It wasn't nearly as bright, as powerful as you would expect, given the unparalleled gamma-ray burst that so spectacularly accompanied it. It was like a tiny engine somehow producing the roar of a jet. To get a clearer, more nuanced picture of this perplexing discrepancy, an unbelievably powerful gamma ray burst from a surprisingly ordinary supernova. Astronomers wisely turned the discerning gaze of the James Webb Space Telescope towards the boat's afterglow. Webb, with its unparalleled sensitivity to infrared light, acts like a cosmic detective with a magnifying glass capable of peering through cosmic dust and stretching light from the early universe. Its near-infrared spectrograph carefully analyzed the faint lingering light, and what it revealed was truly remarkable. The supernova behind the boat was indeed shockingly average. It wasn't nearly as bright or as energetic as one would expect, given the utterly colossal gamma-ray burst that had so dramatically accompanied it. It was like finding a tiny, unassuming engine that somehow powered a colossal roaring inferno. a profound puzzle for even the sharpest minds in the cosmos. So what cosmic trickery, what hidden mechanism could have caused such a blinding flash from such an ordinary stellar demise? One compelling idea gently put forward is that we simply perceived the flash as bigger and brighter because of its relative position to the blast. Imagine, if you will, holding a powerful flashlight in the dark. If you allow its light to spread diffusely soft and wide, it illuminates your path for only a meter or two ahead of you. Now imagine gathering all that light, concentrating it, and focusing it into a singular, incredibly narrow laser beam. This laser wouldn't illuminate the path as widely. No, but its focused brilliance would reach hundreds of meters into the distance, a piercing narrow beam of light. And if Earth happened to be in the direct, precise path of that laser beam, our detectors would register an unbelievably super bright reading, far more intense than what the flashlight with its diffused beam might suggest. This doesn't mean the laser released more total energy than the flashlight, merely that the way its energy was concentrated and then detected from our specific vantage point resulted in a far higher, seemingly exaggerated reading. The same profound concept, it is believed, can be applied to these enigmatic gamma-ray bursts. If a truly massive star is spinning at an incredibly rapid rate, when it finally collapses into a black hole, imagine a cosmic pirouette of unimaginable speed. Then the shape and structure of the near-light-speed jets it emits will be more narrow and highly focused, like that laser beam, and therefore, from our specific angle, they will appear incredibly, impossibly brighter. In fact, the jets seen from the boat are some of the narrowest we have ever seen, like a cosmic needle punching through the darkness. But not only were these particle jets far brighter than expected, radiating with an almost impossible intensity, scientists also detected way more of them traveling with an unprecedented fervor, going faster than expected. They journeyed with such immense power, such unstoppable momentum, that after traversing the vast, dark cosmos for 2 billion years, their faint lingering effects finally arrived here at our home planet and momentarily disrupted the Earth's atmosphere. Sitting just 50 to 1,000 kilometers above the surface of our planet Earth's ionosphere is a crucial layer rich with electrically charged particles. When the boat's powerful high-energy photons struck, they left a distinct mark, a cosmic bruise comparable to that of a major solar flare. This immense energetic impact pushed the ionosphere down into lower, denser altitudes, a tangible tremor from a distant explosion. If photons from an explosion 2 billion light-years away can have this kind of measurable effect on our planet, one might quietly wonder about the implications if something of that magnitude were to explode in our immediate cosmic neighborhood. It's a sobering thought, a reminder of the raw, untamed power that courses through the universe. Adding another layer to this cosmic puzzle, the Large High-Altitude Air Shower Observatory, LHAASOO, in Daocheng County, China, a truly remarkable instrument, managed to capture data on tens of thousands of photons over the course of the initial blast and into the lingering afterglow. This quantity of high-energy photons was utterly unlike anything seen before in gamma-ray astronomy. In fact, it's so far out of pocket, so profoundly anomalous, that some astrophysicists are beginning to quietly suggest that these observations might be pointing towards something fundamental missing from our current models of physics. According to our current understanding of how light, and particularly high-energy photons, travels across the vastness of space, it's very unlikely that these super high-energy photons could travel for 2 billion years without significant interference. The universe is not an empty, pristine void. It's filled with a faint, pervasive hum of cosmic microwave background radiation, the ancient echo of the Big Bang itself. Interactions with this background radiation, or with incredibly dilute intergalactic dust, or even the redshifting caused by the continuous expansion of the universe, are all factors that can interfere with a photon's long, arduous trajectory, subtly depleting its energy or altering its path. Yet, these photons from the boat arrived with astonishing, undiminished energy. One fascinating hypothesis that has been gently put forward to explain this perplexing phenomenon is that these high-energy photons might convert themselves into a hypothetical particle called an axion, while traversing the immense cosmic distances, and then convert back into gamma rays upon reaching our Milky Way galaxy's magnetic field. Axions are thought to be an ultralight particle, a whisper of a particle that some scientists theorize could be responsible for dark matter, that invisible, mysterious substance that makes up the vast majority of matter in our universe. Currently, their existence is purely hypothetical. We have no definitive evidence for them, and even if we did, their existence would lie outside the meticulously constructed standard model of particle physics, which describes all the known fundamental particles and forces. We don't have time to delve into the intricate details of axions in today's gentle cosmic journey. But suffice it to say, this theory highlights the profound interconnected nature of cosmic phenomena and fundamental physics, stretching the boundaries of our current understanding. Okay, so far we've established that the boat was caused by a massive star dramatically collapsing, and in doing so, turning into a black hole, an event known as a collapsar. Aside from generating a long gamma-ray burst of unprecedented power, collapsars are also known for generating something else, something surprisingly precious and tangible: gold. Wait. How you might gently wonder, is something as solid and lustrous as gold connected to a fleeting gamma-ray burst? That's a very good question, and to understand it, let's take a quiet moment to discuss how elements, those fundamental building blocks of everything around us, are made. The core of a star, any star, is an environment of unimaginable pressure, some 200 billion times higher than the atmospheric pressure we experience here on Earth. In these extreme fiery conditions, a process called nuclear fusion takes place. Lighter elements like hydrogen are squeezed and forced together, fusing to create heavier ones. For example, one helium atom, that light noble gas, comes from precisely fusing 4 hydrogen atoms together, a tiny powerful alchemy. Elements from number 2 through 26 on the periodic table, that's everything from helium all the way up to iron, are made this way through a process known as stellar nucleosynthesis, the star's internal forge. However, once you reach iron, the story changes. It isn't energetically favorable to continue making bigger and bigger elements through fusion in the star's core. The process of binding iron nuclei together actually consumes energy rather than releasing it. So this naturally leads us to a profound cosmic question. How do we account for the rest of the periodic table? Where do all these heavier, more complex elements, those precious substances like gold, silver, uranium, and platinum, come from? At the moment, our patient scientific inquiry suggests there are 2 primary distinct ways these elements are formed in the universe, each a testament to the cosmos's vast, intricate chemical processes. The first method was recently beautifully confirmed by the very same James Webb Space Telescope we spoke of earlier. This method involves the cataclysmic collision of 2 ultra-dense neutron stars. Imagine 2 celestial remnants, each weighing more than our sun, but compressed into a sphere only the size of a city, locked in a death spiral. When these unimaginably heavy, incredibly dense neutron stars finally collide, they unleash an immense, staggering amount of neutron particles into the surrounding space. The material in their immediate vicinity, caught in this neutron-rich maelstrom, captures these liberated neutrons, making their atoms temporarily unstable. In order to stabilize themselves, these neutron-rich atoms undergo a process of radioactive decay, gently transforming some of their neutrons into protons, thereby creating entirely new, heavier elements. This remarkable process is known as rapid neutron capture, or the R process, nucleosynthesis. Some scientific calculations suggest that just one such neutron star collision can produce an astonishing amount of heavy elements, up to 3 Earth masses worth of cosmic gold, platinum, and other precious materials, scattered across the interstellar medium like a cosmic dowry. However, this explanation alone, while incredibly powerful, and certainly a significant source, isn't sufficient to account for the entire abundance of all the heavy elements we observe throughout the universe. Neutron star collisions, while spectacular, are relatively rare events, and they take a very, very long time to happen. Often on the order of billions of years, as these binary systems gradually spiral inward. On top of that, meticulous observations of very old stars, those ancient cosmic relics from the early universe, show that heavy elements were already present in significant quantities. In parts of the universe, well before most binary neutron stars would have had a chance to orbit each other for billions of years and finally collide. So how do we explain that? There must be another significant source of heavy elements in the cosmos, another cosmic forge at play, which, my dear listener, brings us back full circle to our enigmatic boat. There's another compelling theory, a fascinating alternative that suggests collapsers like the one that caused the boat could also be another significant source of our process nucleosynthesis. In their dramatic dying stages, massive stars like the one that produced the boat are surrounded by swirling layers of exploding gas, a maelstrom of outgoing stellar material. These cataclysmic explosions leave behind a swirling incandescent disk of matter, gracefully yet violently swirling around the newly formed infant black hole at its heart. As this ravenous black hole begins devouring the surrounding material, it can only ingest so much at a time, like a cosmic vacuum cleaner with a limited capacity. What it cannot manage to ingest is swept away in a powerful neutron-dense wind, a furious outflow of material. Here, in this extreme environment, the same R-process nucleosynthesis occurs, the rapid capture of neutrons leading to the formation of even heavier elements, those precious metals like gold, silver, and platinum. This seems incredibly promising, doesn't it? A second powerful cosmic forge. But alas, even with this intriguing possibility, the universe has a way of introducing further layers of complexity. Unfortunately, detailed analysis of the boat's spectrum did not show any definitive traces of heavy elements, no shimmering gold, no glittering platinum. This absence raises some quiet yet significant questions about the very validity of this collapsar gold-making theory. If collapsars are indeed a primary source of heavy elements, why did the brightest of all time show no such signature? Some scientists, in their meticulous pursuit of answers, have gently suggested that the boat's host, galaxy, the cosmic home where it exploded, might have something to do with this puzzling lack of heavy elements in the explosion. Upon carefully modeling the host galaxy's spectrum, researchers discovered it has the lowest metallicity of all previous host galaxies where gamma-ray bursts were detected. In other words, perhaps the environment itself, the very cosmic soup from which the star formed, simply didn't have the right basic building blocks, the precursor elements to make these heavier elements in the first place. It's a subtle but crucial distinction. How do we even know, you might softly ask, how much gold should be out there in the first place? How do scientists, with their meticulous calculations, predict something as grand and fundamental as the relative abundance of elements in the universe? It's a profound question, one that delves into the very chemical history of the cosmos. There are primarily two main methods, two patient cosmic detectives that help us calculate this intricate cosmic inventory. The first method involves the careful spectroscopy of stellar photospheres. Imagine looking at the shimmering outer layers of distant stars, their photospheres, through a cosmic prism. When starlight passes through the gases in a star's atmosphere, certain wavelengths of light are absorbed by specific elements, leaving behind dark lines in the star's spectrum, like a unique barcode. By meticulously analyzing these intricate absorption lines, astronomers can determine the precise relative abundances of various elements present in the star's outer layers. Each star, in essence, becomes a living fossil, preserving a record of the chemical composition of the cosmic cloud from which it formed. The second method involves the careful analysis of meteorites. These rocky visitors from space are often pristine remnants of the early solar system cosmic time capsules preserved in ice-cold vacuum for billions of years. Their composition is analyzed in parallel with stellar data to determine the relative abundances of elements, Meteorites are especially useful for measuring the abundances of volatile elements like hydrogen, helium, and the noble gases, which are often underrepresented or difficult to measure accurately in stellar photospheres. The results of both of these meticulous methods are usually wonderfully congruent, meaning they largely agree, indicating that our scientific models are probably doing something fundamentally right, piecing together the universe's chemical story with a reassuring consistency. But this is physics, my dear listener, and of course, nothing is ever quite so cut and dry. The universe, in its boundless complexity, loves to introduce elegant, perplexing exceptions. One famously stubborn exception to this reassuring rule is lithium. According to the carefully constructed standard Big Bang nucleosynthesis theory, our best model for what happened in the very early moments after the universe began, the primordial universe should have produced about 3 times more lithium-7 than is currently observed in the oldest stars. It's a curious deficit, a missing piece in the cosmic puzzle. And the plot thickens even further when we consider its rarer isotope, lithium-6, where we actually observe 1,000 times more than our predictions can account for. It's a profound excess, a cosmic oversupply. This perplexing discrepancy, this cosmic imbalance, is known as the lithium problem, and it remains stubbornly unsolved, presenting a significant and beautiful challenge to the standard cosmological model. It highlights the profound importance of truly understanding the intricate processes that shape the relative abundances of elements in the universe, and it gently suggests that our current understanding of nucleosynthesis, the cosmic art of making elements, might be beautifully incomplete. There are still deep secrets waiting to be unveiled in the cosmic forge. Just because the boat in its blinding unique brilliance didn't yield gold as perfectly expected, doesn't mean we should simply discard these kinds of extreme gamma-ray bursts as potential places where heavy elements could be made. The universe is vast and full of surprises. Observations of nearby stars, for instance, have provided strong, tantalizing evidence for an early R process that enriched the universe with heavy elements very early in its history, perhaps from events that predate most neutron star mergers. But the boat's findings, with its puzzling lack of heavy elements, cannot be ignored either. They gently suggest that there may be alternative, currently unknown processes responsible for the elemental enrichment of our cosmos, other hidden cosmic alchemists at work. The results from the boat, in their profound implications, may even call into question our entire established model of understanding. Regarding collapsers and their precise role in creating heavy elements, this discovery, this single perplexing event, is much bigger than just the boat or the specific details of gamma-ray bursts. It's about the literal building blocks of our universe as we know it. Where do our different atoms, those fundamental particles that form everything from the air we breathe to the stars we gaze upon, truly come from? And why do they exist in the precise proportions they do? How much of our current cosmic model is accurate, beautifully precise, and how much is still missing? Waiting to be discovered, what role does that elusive, invisible dark matter play in all of this, if any? We need more time, more patient observation, and more dedicated research before we know for sure. But the boat, in its perplexing glory, is a truly magnificent example of how new findings, new whispers from the cosmos, continually keep our understanding of physics ever evolving, ever expanding, much like the universe itself. It's a journey of endless curiosity, a constant unfolding of profound truths. Imagine for a moment, as you drift deeper into cosmic contemplation, that you're looking out your window on a clear, dark night. Suddenly, a singular, intensely bright light flares into existence in the sky above you. This dazzling, unexpected star is as luminous as the full moon, perhaps even brighter, so brilliant that it's even visible during the day. If you can see the light so vividly, you might already be in profound trouble. That unexpected celestial visitor is now flooding the atmosphere of the Earth with a catastrophic dose of gamma radiation and X-rays, stripping away our fragile ozone layer, and exposing us to the full unbridled fury of the sun's deadly radiation. And on its way, jettisoning outwards at speeds of 10,000 to 40,000 kilometers per second, a cataclysmic wave of stellar matter and debris hurtles towards our planet. This is the dying roar of an exploding star, venting billions of tons of burning mass at us, ready to sweep across our planet's surface in a literal tidal wave of fire. This, my dear listener, is a supernova. Or at least, it's one chilling, dramatic interpretation of what we might see and experience if one were to occur truly near us. But how likely is it for this dramatic, terrifying scenario to actually happen? What, on a cosmic scale, truly constitutes near us? How close would a supernova blast truly have to be before life on Earth, in all its precious fragility, would be genuinely threatened? What might we here on our tiny blue planet actually experience? And perhaps most importantly, what stars, those familiar pinpricks of light in our night sky, have the potential to detonate in such a cataclysmic way, transforming into these blazing transient beacons of cosmic power? I invite you now to join me as we gently discuss an event that could theoretically be an Armageddon in our lifetimes, or could be nothing more than a particularly pretty, albeit distant, twinkle in the night sky. The universe, after all, holds both profound beauty and unimaginable power. Let's begin with a comforting thought, a piece of good news to ease any cosmic anxieties. Supernovae, those colossal stellar explosions, are mercifully not that common in our own galaxy, the Milky Way. While astronomers diligently observe hundreds of supernovae every year in galaxies far, far beyond our own in the Nimbus, it is mostly a reflection of the sheer, unfathomable number of galaxies that populate the vast, expanding universe. Closer to home, though, within the swirling arms of our very own Milky Way, we likely only witness about 2 to 3 such events every century. This means that the odds of one dramatically going off tomorrow, right in our backyard, are thankfully not that high, a reassuring thought as you drift to sleep. But importantly, they're not entirely impossible either. The universe, as always, holds its quiet surprises, and according to patient archaeologists who sift through the geological layers of our planet's past, Earth has very likely been hit by the lingering echoes of a supernova before in the course of its incredibly long 4.5 billion years of existence. For starters, we as inhabitants of this planet exist in a rather unique and comforting area of space known as the local bubble. This is a relatively sparsely populated region of interstellar space, a vast quiet cavity about 1,000 light-years across. It is thoughtfully believed to have been carved out, swept clean by a powerful supernova detonation that occurred a staggering 10 to 20 million years ago, an event that our planet would have quietly witnessed from a safe distance. I've explored this fascinating cosmic neighborhood in another of my journeys, a testament to the universe's ancient unseen sculpting. Scientists have also unearthed compelling evidence of another detonation, a fainter cosmic echo that occurred roughly 2.5 million years ago. This evidence comes in the form of a notably high concentration of iron-60 and manganese-53, found in a particular ancient layer of the geological record here on Earth. Iron-60, in particular, is a radioactive isotope that is not naturally produced on Earth, but is a telltale signature of supernova ejecta, the material expelled during a stellar explosion. This ancient supernova, while leaving its faint chemical fingerprint, happened far enough away to be utterly harmless to us, a distant, magnificent flash that posed no threat. But this might not always be the case. And here, the narrative takes a more speculative, yet intriguing turn. There are some scientists who quietly believe that the puzzling extinction of the woolly mammoths, those magnificent shaggy giants of the Ice Age, might have been partly caused by a massive piece of debris from a supernova, a cosmic projectile crashing into the planet about 13,000 years ago. The impact site in question, a potential scar from this ancient event, contained magnetic spherules and traces of radioactive potassium-40, another substance often found in supernova ejecta. If true, It would be a true smoking gun in the era when most mammoths mysteriously went extinct, a cosmic twist in their tragic tale. Even before that evidence suggests that mammoth tusks from 34,000 years ago were found containing tiny impact craters from microscopic grains of slightly radioactive iron that had been traveling at speeds of 10,000 kilometers per second. If you can recall, that was one of the potential speeds at which supernova explosions travel. That certainly can't have been a nice experience for the mammoths. In question, a shower of cosmic shrapnel. An astute observer, a thoughtful listener from all this, might be able to note an important, reassuring fact, however. Evidently, if life began on Earth about 3.7 billion years ago, and we have potentially faced 3 supernova explosions that have impacted us in some way in the last 20 million years, and life is still largely ticking along, thriving in its diverse forms. With my deepest condolences, of course, to the woolly mammoths, if you indeed did die out from one of these, then supernovae as a whole can't be quite as universally destructive as my opening introduction might have made them out to be. And that, in large part, is wonderfully true, although it is, of course, fundamentally a question of proximity. Imagine, if you will, the sheer power of a nuclear bomb. If I'm 1,000 kilometers away from one going off, I have little to fear, merely perhaps a faint rumble. But it's an entirely different story, a terrifyingly immediate one, if one were to detonate on my coffee table. And when it comes to supernovae, those colossal cosmic detonations, it turns out that the universe has relatively large coffee tables, vast stretches of emptiness where their furious energy dissipates harmlessly. To truly understand the scale of these explosions and why proximity is so crucial, it's necessary to understand a little better the immense forces involved, which means we need to understand a little more about how supernovae actually happen. The universe, in its wisdom, has 2 main paths, 2 dramatic finales that stars can take to reach that explosive, incandescent crescendo. Although in each case, it has to be precisely the right kind of star, a cosmic giant, for the show to begin. For the first path resulting in a type Ia supernova, it usually needs to be a white dwarf in a binary system. Imagine a white dwarf as the dense ultra-compact remnant of a star like our Sun after it has shed its outer layers. It's essentially a stellar cinder roughly the size of Earth, but packing the mass of the Sun. In a binary system, this white dwarf is locked in a gravitational embrace with a neighboring star. This companion star might be a bloated red giant, or even another smaller star. The white dwarf, with its immense gravity, gradually or sometimes quite speedily, begins siphoning matter away from its companion, like a cosmic vampire drawing sustenance. It slowly accumulates this stolen stellar material until it reaches a crucial point, a critical mass. This path to explosion, the exact mechanisms are not yet fully understood and remain a fascinating area of cosmic inquiry. But the prevailing thought is that a white dwarf, which is an incredibly dense star primarily comprising carbon and oxygen, essentially a giant superdiamond core, is normally held in a delicate precarious balance between 2 incredibly powerful opposing forces. On one side, there's electron degeneracy pressure. This is a fundamental quantum mechanical effect where the electrons within the white dwarf object are being squashed too much. They fiercely resist being pushed denser than a certain point, maintaining a quantum barrier. On the other side, there's gravity, an incredibly powerful and relentless force that constantly seeks to draw matter closer, to crush it into an even denser state, particularly in a dense mass like a white dwarf, where a section the size of a sugar cube can have the astonishing mass of an entire car. And so in a binary system, where the white dwarf is absorbing more and more matter from its unsuspecting neighboring star, its internal pressure steadily increases. Eventually, the relentless, overwhelming force of gravity triumphs over the electron degeneracy pressure. The delicate house of cards, the exquisite balance collapses all at once. The white dwarf, reaching its critical mass, suddenly ignites. Carbon fusion, a runaway nuclear reaction that was previously held in check, begins rapidly throughout the star. Within a few breathtaking seconds, most of the star undergoes runaway fusion, swiftly transforming its carbon and oxygen into much heavier elements, and in doing so, releasing an unimaginable colossal amount of energy. It's an instantaneous blinding inferno as the matter in the star settles into a slightly more efficient, tightly bound new configuration. How much energy, you might wonder, is released in such a colossal, instantaneous cosmic firework around 1 quatuordecillion joules. That's 1 followed by 45 zeros. If you claim you knew that number before, my dear listener, you are almost certainly a magnificent liar, or perhaps a secret cosmologist. All of this truly unimaginable energy is released in just a few short seconds. Naturally, the star doesn't just quietly implode. It violently ejects its entire contents outwards in all directions, sending it traveling at an astonishing 6% the speed of light. And as it explodes, it unleashes a colossal flood of high-energy radiation, predominantly gamma radiation, out across the galaxy. The sheer blinding brightness of this event is truly astounding, shining an incredible 5 billion times brighter than our Sun. This incandescent blaze typically burns for a few weeks, its light slowly dimming as the ejected stellar material has traveled far enough that the overall energy level of the blast has started to dissipate into the vastness of space. The second type of supernova, known as a Type II supernova, is similar in its explosive grandeur, except instead of involving a white dwarf, it involves a truly massive star, one at least 5 times more massive than our Sun. These colossal stars live fast and burn incredibly brightly throughout their lifetimes, fusing lighter elements into heavier ones in their cores. And rather than just electron degeneracy pressure holding the star in delicate balance against gravity in these massive stars, it's also the fierce outward push from the heat and energy generated by nuclear fusion in their cores that keeps the star from collapsing under its own immense weight. However, just like a Type Ia supernova, eventually, the star's internal balance dramatically collapses. This time, it's because the massive star quite simply runs out of fuel for its core fusion. Without this additional powerful fusion energy pushing the star's immense mass outwards, the electron degeneracy pressure on its own simply cannot cope with the star's overwhelming weight. The core rapidly collapses, triggering a colossal rebound explosion. The effect is similar in its dramatic destructive power, a star tearing itself apart in an instant of blinding light. The only difference is that while some of a massive star's original mass will remain behind, often collapsing down into an incredibly dense neutron star, or a ravenous black hole, white dwarfs in their Type Ia explosions usually vanish completely, leaving behind only an expanding shell of light and gas. Either way, whether it's the sudden fiery reignition of a white dwarf or the core collapse of a massive giant, the sheer scale of material and energy released by supernovae is truly vast. So vast, in fact, that it comes as no surprise that anything immediately next to such an event is simply not going to last long. This is an energy powerful enough to literally rip apart an entire star. A mere planet would have absolutely no chance if it were unfortunate enough to be in the immediate vicinity. Our own Sun, thankfully, will never go supernova, as it's simply not massive enough to do so. It will instead swell into a red giant and then slowly fade into a white dwarf. But if it did go supernova, there is a very good chance that Earth would be either partially or completely vaporized. Its rocky exterior would reach a searing boiling point thanks to temperatures 15 times hotter than the surface of our Sun, and our planet would then be unceremoniously whisked away into the expanding violent stellar winds and debris in the weeks following the supernova's passing. What is perhaps surprising, however, is how quickly this first devastating wave of pure destruction would dissipate with distance. Indeed, complete vaporization is realistically not the largest or most common threat that supernovae pose to distant planets. In 2011, brilliant experts from the University of Cambridge meticulously calculated that even planets orbiting their star at a vast distance of 15 billion kilometers which is about 100 times the distance between our Sun and Earth, would likely remain intact. They wouldn't be vaporized. Instead, they would simply be sent flying gently, but irrevocably, out into the cold, dark emptiness of interstellar space, adrift in the cosmic ocean, now that there was nothing much left for them to orbit. Of course, such a planet's hypothetical ecosystem would probably have vastly different, more immediate problems to worry about. Things would get very, very cold, very, very quickly. Of course, even if the solid crust of a planet itself remained intact, that doesn't necessarily mean that life on said planet would be sustainable. Ignoring the initial blinding light of a supernova, which could easily outperform the brightness of an entire galaxy, sometimes leading to permanent blindness. For anyone who happened to witness it, simply stripping away our atmosphere would carry profound existential problems. High levels of radiation, even if they didn't directly affect us with immediate lethality, would drastically alter the chemical composition of our atmosphere, negating our precious ozone layer. This would vastly increase our odds of dying from direct radiation poisoning, and more broadly, would decimate our delicate phytoplankton in the ocean, those microscopic engines of life that form the base of the marine food chain. This in turn would cause mass extinctions, as the profound consequences of that ecological collapse worked its way up the entire food chain, profoundly reshaping life on Earth. Scientists generally put this immediate kill zone, where such effects would be catastrophic, to be within about 25 light-years. Beyond that distance, the fury of a supernova begins to calm considerably, as the immense cosmic distances cause its energy and destructive power to wear itself out, to diffuse into the vast emptiness. Although, admittedly, the asteroids that potentially killed the mammoths came from a supernova that was roughly 250 light-years away. If that theory is true, it was likely an incredibly unlucky hit, a rare cosmic billiard shot. Generally speaking, however, we wouldn't notice any significant damage from a supernova this far away. Its radiation levels simply wouldn't be high enough to cause mass extinctions. By 500 light-years away, we'd hardly notice the event at all, other than perhaps seeing a surprisingly brighter, new star in the night sky, a beautiful distant spectacle rather than a terrifying threat. This brings us to one immensely important, reassuring question. Within 300 light-years of us, are there any supernova candidates, any ticking cosmic time bombs that we need to worry about? Thankfully, scientists are fairly confident that the answer for the foreseeable future is a resounding no. Massive stars, the ones that produce Type II supernovae, are very noticeable. They are bright, luminous giants, easy to spot and track. The only two truly massive stars in our immediate cosmic neighborhood that are at theoretical risk of eventually going supernova are Betelgeuse in Orion and Antares in Scorpius. Both of these magnificent red giants are more than 400 light-years away from us, comfortably outside that 25 light-year kill zone, and even the 250 light-year mammoth zone. They are distant spectacles, not immediate threats. White dwarfs, on the other hand, those potential Type Ia supernova progenitors, are a little trickier. Thanks to their diminished brightness and small size, they have conventionally been very hard to spot, making it harder to predict whether we might be at risk from them. However, in 2013, ESA's brilliant Gaia Space Observatory released a massive, unprecedented packet of information in its ongoing efforts to meticulously map the stars in our galaxy. This incredible data set allowed scientists to identify a staggering 13,000 white dwarf stars within 326 light-years of us. A large number indeed. But thankfully, in spite of this seemingly large number, scientists remain confidently reassured that none of these identified white dwarfs are scheduled to explode anytime soon. And by soon, in astronomical terms, we mean within the next few 100,000 years. So, you can rest easy on that front. Speaking of Betelgeuse, that familiar red giant, there are some scientists who predict that this star, with its dramatic fluctuations, might detonate much sooner than the usual timeline for such a massive star, perhaps even within the next few decades. Their research works under the fascinating assumption that Betelgeuse has a much larger radius than previously predicted. But if it's true, it might mean that we would indeed get to see a local supernova within our lifetimes, a true once-in-a-species event. Of course, according to some models, even if Betelgeuse were to explode, we would have absolutely nothing to worry about here on Earth. The shockwave traveling out from Betelgeuse, immense as it is, would take some time to get to us. And even once it finally arrived, it would be traveling with less force, less impact than the gentle push of our own solar wind from the sun. In other words, it wouldn't be Earth's magnetosphere or our atmosphere that kept us safe. The protective sheath of the sun's own heliosphere, that vast bubble of solar wind that envelops our solar system, would be more than enough to keep such a distant supernova at bay, a testament to our sun's gentle, unseen protection. So there you have it, my dear listener. While supernovae are perhaps some of the largest, most violent explosions in the universe, true cosmic spectacles, through some fortunate stroke of cosmic luck and our strategic location, our patch of galaxy has nothing truly significant to fear from them. The odds of us being hit by even the neighboring stars like Betelgeuse that are scheduled to go supernova are incredibly reassuringly small. True Earth has plenty of cataclysms of its own, such as floods, earthquakes, and hurricanes, that can bring devastation to a community in a heartbeat, and space is still undeniably a dangerous place full of powerful, unpredictable phenomena. But it's nice to know that of all the profound things we have to worry about, we can probably cross planetary annihilation from a supernova off our list, and instead simply marvel at their distant, silent beauty. As we gently begin to wrap up our journey through the cosmic unknown, let us briefly contemplatively touch upon one final tantalizing question that has fueled human curiosity for centuries: the search for alien life. It is a difficult search, fraught with ambiguity and immense distances. How in the vastness of the cosmos would we even know that aliens exist? An obvious answer, a dramatic cinematic one, would be if they visited our planet en masse. If, like in the film Independence Day, their colossal saucers floated ominously above every city in the world. Or perhaps if their envoys, their first gentle ambassadors, met with us shaking hands with our world leaders while cameras broadcasted the momentous occasion on national television. Or maybe more practically, if they started trading with us and their incredible inventions and boundless resources began appearing in our everyday lives, subtly woven into the fabric of our civilization. There is fortunately, or unfortunately, not much credible evidence that this has ever happened, at least not in any overt, undeniable way. But while direct, undeniable visits from aliens would certainly be preferable for immediate confirmation, that's not the only possible way aliens could prove their existence to us. It's far more plausible, far more subtly profound, that they would do so with their signals. Faint whispers across the cosmic ocean, a message sent into the void. We've spent a lot of time in these quiet contemplations discussing some of the reasons why aliens might not have talked to us yet. The vast distances, the brevity of civilizations, the immense challenges. But on the flip side, what are the strongest pieces of evidence, the most tantalizing clues that they have already done? So, which signals, those faint echoes captured by our sensitive instruments, are considered the best candidates so far for a message from an alien civilization, a true whisper from another world? I invite you now to join me as we gently ponder where perhaps we already have heard from them. Obviously, when it comes to alien signals, there is a profound ambiguity as to what exactly we are looking for. Aliens are, after all, fundamentally alien. We are not quite sure what to expect from them, for they will have likely evolved in conditions vastly different to our own, shaped by different suns and different gravities, and they may well possess cultural outlooks, ways of thinking, that make perfect elegant sense to them, but are completely obscure, utterly bewildering to us. Their definition of a good way to say hello to the universe might be very different from our own. Researchers diligently looking into possible signals from other planets must remain incredibly open-minded about what an extraterrestrial signal might look like embracing the unexpected. But that very openness means that such signals can sometimes get confused with signals from natural cosmic sources that we simply do not yet fully understand. How then can we tell the profound, delicate difference between a natural cosmic hum and a deliberate, intelligent whisper from afar? Let's look at a few examples to gently illuminate what I mean. In 2019, as part of the ambitious Breakthrough Listen initiative, a global effort to systematically search for signs of intelligent life, the Parkes Murray-Young telescope in Australia was patiently observing Proxima Centauri, the closest star to our own, a mere 4.2 light-years away. Its primary mission was to record data to learn more about subtle stellar flares emanating from this nearby star. But when SETI researchers, SETI being the collective term for the search for extraterrestrial intelligence, meticulously went over the data it had collected some time later, they found something truly unusual, a signal, a persistent, narrowband whisper, which later came to be known as BLC-1. Could the star closest to our own actually harbor advanced alien life? The thought was profoundly thrilling. The signal was fascinating precisely because it could not be easily explained away by conventional terrestrial sources. It lasted for several hours, which is significantly longer than the time it normally takes for a human satellite to pass by, overhead eliminating a common source of interference. It also exhibited signal drift. Its frequency was subtly shifting, which implied possible movement relative to the telescope, suggesting it likely wasn't coming from a stationary object, creating interference on Earth. One of the most compelling things BLC-1 had going for it, the detail that truly made scientists lean in closer, was its thin, narrow band signal. In nature, radio waves are almost never so exquisitely narrow in their frequency range. They always fluctuate, broadening slightly, unless there exists some natural source out there we've not yet discovered, a completely unknown cosmic phenomenon. The only thing that consistently produces such a precise, concise signal as this is technology, whether it be human or perhaps alien. When no obvious explanations for its existence could be found amongst known human sources, naturally scientists gently wondered, could this finally be the signal from alien life they had been diligently searching for so long? Along with the famous WOW signal, which we explored in a previous cosmic journey, BLC-1 is considered one of the strongest candidates for signals that may have been created by genuine alien civilizations. And yet even this signal, so promising and captivating, had its subtle drawbacks, its lingering ambiguities. Scientists, despite their meticulous efforts, could not definitively link it to any sources of obvious interference from technology on Earth. However, closer, even more rigorous examination of the data revealed that it did subtly match other radio wave signatures that mysteriously cropped up on other days of the search. Crucially, these other signals occurred no matter what direction the telescope was pointing, in suggesting a terrestrial origin, perhaps some subtle unknown electronic interference within the observatory itself. Neither, unfortunately, were they able to detect BLC-1, this tantalizing signal from Proxima Centauri, with later follow-up observations, despite repeated hopeful attempts. So while they don't know exactly what interfered with the telescope to produce BLC-1, the odds of it being some form of subtle interference, a ghost in the machine, are nonetheless quite high. The universe, it seems, enjoys playing coy. Let's now take a look at another intriguing candidate, one with a somewhat less poetic, more technical name, SHGB-H2-A. When one of the very first SETI experiments, the pioneering Project Ozma, was started in 1960 by the visionary Frank Drake, it began with a very specific, thoughtful hypothesis. Drake reasoned that if alien life were ever to purposefully communicate with the rest of the universe, they would most likely do so at a frequency of 1420 MHz. The elegant logic behind this choice was that this precise frequency is commonly emitted by hydrogen, the most widespread and abundant element in the entire universe, aliens looking to establish communication with other civilizations. Drake surmised might use such a universal frequency as a sort of common ground, a cosmic beacon, a wavelength that probably holds a special fundamental significance to any intelligent race anywhere in the cosmos. This might have been a leap of logic, perhaps a hopeful assumption, but it certainly made SHGB 2 plus A of profound interest later, because this signal, let's just call it SHG for the rest of our gentle journey for the lack of a catchier name, did indeed broadcast at this exact auspicious wavelength. SHG was spotted on 3 separate occasions in 2003, detected by the colossal Arecibo telescope, that magnificent dish nestled in Puerto Rico, and processed with the immense computational power of 5.2 million home computers as part of the fascinating SETI Home Initiative. This was a rather cool distributed computing program that sadly is no longer running, but once allowed ordinary people to contribute their idle computer power to the search for extraterrestrial intelligence. SHG, much like BLC-1, had no obvious clear explanation for its origins in nature. It didn't appear to be interference from a known human source, which for SETI researchers is always the first, most crucial step in the elimination process. But it was also too weak, too faint, to say for sure whether it was definitively technological or simply an undiscovered natural phenomenon, a quiet, unfamiliar hum from the cosmos. On top of that, its location was peculiar, a true cosmic head-scratcher. It came from a spot in the sky utterly devoid of stars for up to 1,000 light-years away from Earth. If it were truly from an intelligent civilization, where would they be? And although it experienced signal drift, that subtle shift in frequency, it did so in a manner that made scientists suspicious, raising more questions than answers. If a signal truly originates from a planet, then there are a few things we might reasonably infer about its behavior. A signal being broadcast from a planet, whether from its surface or in orbit just above it, would likely experience some predictable Doppler shift. This shift would occur as the planet alternately moved away from us and then came towards us through its circular orbital path in space, creating a characteristic frequency change. There would also be predictable moments where the signal would drop out of view entirely as the transmitting planet moved behind its host star, or even behind its own bulk, briefly blocking the signal. While SHG did indeed experience fluctuations in its signal frequency, ranging from 8 to 37 Hz per second, this pattern would only come from a planet that was rotating an astonishing 440 times faster than Earth. That seemed incredibly, impossibly high, far beyond the rotational speeds of any known stable planet. It was also profoundly strange that each time the signal was spotted again on subsequent occasions, no matter where the telescope had been pointing when it had last been sighted, it always miraculously began broadcasting at precisely 1420 May years. The odds of you looking at an orbiting transmitter on 3 separate occasions, and each time spotting it starting off at the exact same location in its orbit, the precise moment it would align to transmit at that exact frequency, is incredibly slim, almost zero. This particular observation of this peculiar reset in frequency strongly pointed to it being more likely that SHG was some kind of glitch in the technology, a subtle internal quirk of the instrument or its processing, rather than a genuine extraterrestrial beacon. By looking at the meticulous process by which the BLC-1 or the SHG signals were evaluated, we gain an interesting, profound insight into how SETI determines whether something might genuinely be of alien origin. To me, it is a method that lines up beautifully perfectly with a timeless quote from Sir Arthur Conan Doyle, articulated by his famous detective Sherlock Holmes. When you have eliminated the impossible, whatever remains, however improbable, must be the truth. Each time researchers came across a new intriguing signal, they began by eliminating all possible known alternatives. Could it be interference from a passing satellite, a distant radio signal, or a terrestrial electronic hum? Is there anything in nature that we know of that could be producing this specific effect, this precise signature? Can we in any other way explain why this signal is here and behaving in the peculiar way that it does? So far, with patient diligence, alternative explanations have been found for these compelling contenders for alien communication. Even on the occasions where human interference can be definitively ruled out entirely, that still leaves open the profound possibility that these mysterious signals might just be undiscovered natural phenomena, new cosmic whispers that we simply haven't learned to categorize yet. And that, my dear listener, is precisely the current discussion swirling around the last and perhaps most intriguing candidate for alien signals I'd like to leave you with today: fast radio bursts, FRBs. Imagine for a moment that if an alien civilization were ever to be truly detected, it might not even be intentional on their part. Perhaps the activation of immensely powerful engines, or the firing of colossal beams for interstellar travel, or the operation of advanced technologies might inadvertently release bursts of energy that to us would give away the presence of a truly galactic civilization. This very idea is what makes fast radio bursts, or FRBs, so profoundly interesting. They are, just as their name suggests, incredibly fast bursts of radio waves lasting only a few milliseconds, yet containing immense energy. We have detected hundreds of these strange fleeting blips across the sky. Scientists theorize that there might be thousands, if not tens of thousands of them occurring every single day across the vastness of the universe. They have mostly been detected originating outside our own Milky Way galaxy from incredibly distant cosmic sources. But one was indeed detected within the Milky Way in 2020, suggesting they are not completely foreign to our galactic neighborhood. They seem to be coming from extremely powerful magnetic fields, and as of yet, scientists have no clear definitive idea about what their ultimate origin might be. There are plenty of theories, of course, swirling in the cosmic winds. Perhaps they are emitted by highly magnetized neutron stars, known as magnetars, undergoing some unknown violent process. Or maybe they are tied to enigmatic black holes in some way we don't yet understand. But for now, there is no definitive proof that puts any one theory above another, including that tantalizing, improbable one of alien technology. The CHIME telescope in Canada, with its unique and innovative design, is ideally suited for detecting these fleeting blips in the cosmos. Unlike traditional dish telescopes that must be pointed at a single point in space, CHIME's multiple cylindrical parabolic reflectors are able to draw data from an entire swath of the sky, at the same time acting like a vast, passive cosmic ear. It began detecting FRBs in 2018 and is still going strong to this day. It has detected FRBs that are repeating, sending out multiple bursts, as well as one that is definitely associated with a known magnetar. Perhaps all FRBs can eventually be associated with such stars, or perhaps not. But that is precisely the point, the heart of the mystery. Perhaps one day we will indeed be able to definitively identify the origin of all FRBs, and we will know with a comforting certainty that they all have a perfectly natural, though perhaps spectacular origin. Perhaps then, the active search for alien life for that definitive whisper will have to begin afresh with new hypotheses and new instruments. But there is always that tantalizing hope, that slim, beautiful possibility that one day a scientist in the meticulous process of ruling out signal after signal will finally receive one that defies all alternative explanations. If all other explanations can be ruled out, if we can say for certain that no known natural source, no terrestrial interference, no technological glitch caused this particular signal, then in the profound, elegant words of that great detective, we will have no choice but to accept the improbable. So these, my dear listener, are some of the best candidates we have so far for signals from another planet, for those elusive whispers from the cosmic ocean. But even they, captivating as they are, come with massive lingering uncertainties. We have not yet found a signal that conclusively, undeniably points to the existence of aliens, to a distant intelligence sharing this vast universe with us. But that in its beautiful ambiguity is not to say that we never will. It's never aliens, right up until the moment where perhaps it truly is. As we gently bring our cosmic journey to a close, I want to express my deepest gratitude. I was honestly blown away by all the incredibly kind comments and heartfelt messages you've sent me, and by the sheer numbers of you that have signed up to the Patreon. Like I've said in the replies to your DMs, everyone here at the Astrum team is so incredibly grateful to have such an amazing, curious, and supportive community. If you haven't joined the Patreon party yet, we're still on our long-term 1,000 Patreon member drive, so you can go to the link in the pinned comment to become a part of that effort. When you join, you'll be able to watch the whole video, ad-free, see your name in the credits, and submit questions to our team, becoming an even more integral part of this cosmic exploration. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time under the same vast, mysterious sky.